Okay, good morning, everybody. Thank you for being here. Very brave, very good. We'll have a very exciting session on interiors today. Just as a reminder, after this interior session, we have one additional surplus flash talk session because we got so many exciting flash talks from the posters. And so these are the people who will present in this poster flash talk session, which is after this first interior session. And with this, then maybe we can, can you switch over? So we'll start with the interior session. And the first talk will be presented by Yoshi Eschen on tracing refractory abundances from stars to rocky planets across the galaxy. You have 10 minutes, and we look forward to your talk.
Thanks. Cool. Good morning. Thanks for being here after this very, very long conference dinner, but thanks a lot also for the organization. I think we all had a lot of fun. I'm Yoshi, just like in the Mario game, and I'm like a first/second year PhD student at the University of Warwick. Right now I'm working on La Palma, observing for ING. So this is, however, still my PhD project I'm presenting. And we've heard a couple of times already during this conference that there seems to be a link between planets and stars. So here I'm showing a plot by Haiyang Wang, where we see the compositional link from refractory elements between the proto-sun and Earth. And on the very right-hand side of that plot, we see the refractory elements, which are for the yellow sun and the blue Earth, very similar. For volatiles, this is slightly different. And there's a proposed similar link also for stars and their orbiting exoplanets. This means that also planets around metal-poor stars should have less refractory elements and hence be less dense. However, this is kind of hard to really show because there's not many planets orbiting metal-poor stars. So this is mainly what we're focusing on here. And this now is a plot by Vadan Adibekian, who kind of tried to explore this link in 2021. And he was just like looking at small rocky-ish planets and identified two clusters, the super Mercuries, which we see at the top at high density, and the super Earths, which might be following some kind of proportional trend here, although this is mainly ruled by this one outlier at a F iron star of 25%. So on the x-axis, we have the stellar iron to silicate mass fractions, and they represent how metal-poor and alpha-enhanced stars are. So everything that is really low here means the star is metal-poor, and yes, we only have 1 point, which is kind of the challenge of this. Just also for reference, at like 33, this is where the sun lies and also the majority of planet-hosting stars. So we now try to explore or find more planets orbiting metal-poor stars. And so for this, we were just like looking at the Apogee DR17 data, which is publicly available. And I'm just plotting this here on an alpha FEH diagram. And we can quite nicely see two clusters. So we have a lot of stars which are like at kind of-ish solar metallicity, which is a really big cluster. And this is also chemical, mainly the thin disk. But we also have this other cluster, which is slightly less stars, but still like a cluster we can definitely identify, which is more alpha-enhanced and more metal-poor. And this is the chemical thick disk. And I just like cross-matched this apogee sample with known planets and also computed their kinematics. And this is just like the color coding in there. But we can see the majority of confirmed planets lie in this bottom cluster and are also kinematically purple, so in the thin disk. And we have a massive lack at the higher up cluster. So just to identify stars in these clusters now, we started to just like use machine learning because we can see these clusters by eye. But actually to go after stars where we can show that they lie in one cluster and try to apply this then also to other stars, we try to do it with machine learning. And so I'm just like showing the different plots here. So this is the one cluster we can pick up with machine learning, which also aligns with the kinematics. So we see the same trend kinematically, that the stars in this cluster also kinematically in the thin disk. We have the same for the thick disk. And then we have some outliers, which are kind of also the halo. So a lot on the left-hand side of this plot is the halo. However, the machine learning also picks up the other stars just because the sample of these stars are really, really small. In the end, we don't really care about the halo, so it's fine if it just picks up the scatter, because in the end, we very nicely want to identify the thick disk, which is the green cyan-ish cluster we have here, which it does pick up. Here, I'm just like plotting cluster probabilities of above 70%. So this is why we have the white lines in there. There are stars in between. There's not a lack of stars in these white lines, just to clarify this. And with this, we just like started to look at some more kinematically or chemically interesting new targets. So the first one I will present is in a paper I published last year, which is a thick disk target. It's 2 planets orbiting 2I2345, which is a K-dwarf. It's slightly metal poor and alpha enhanced and has a kinematic thick disk probability of 85%. So I'm showing it on the tumor diagram where it lies in the purple area. It is the star at like V of -100. So kinematically, it's in a thick disk, and it's also slightly metal poor and alpha enhanced. So quite an interesting target for us to study. It was found by TESS. We followed up with KOPS, so we got quite precise planetary radii. We found it in a super-Earth, which is of an ultra-short orbital period of 1 day, and an outer sub-Neptune at 21 days. I'm just showing our TESS transits and the KOPS transits here. And then we also followed up with HARPS in order to characterize the masses quite precisely. And from this, we could get nice densities and perform our interior structure modeling. For the interior structure modeling, now we were using Planetic, which was written by Joanne Agger and is using deep neural networks to determine the planet interior structures. And for this, we can kind of apply different stellar abundance links. So we were using either just like the stellar abundances, also for the priors on the planetary abundance. We can use slightly iron-enhanced abundances, which was also suggested by Vardan Adibekian, or just a uniform distribution. And we now also added exoint, which was developed by Haiyang Wang, who gave a talk, I believe, on Tuesday, which is basically devolatilizing the star, and we use this as a prior. And the stellar priors are A1, and our exoint priors are A4, and we can see quite nicely that they overlap, which is kind of also reassuring that there's not much difference in the refractory elements here. However, if we actually use this devolatilization prior, we're able to slightly better constrain the different mass fractions. So that was also actually quite nice to see. We then moved on to another interesting target, which was now still in prep, and this is 2A4311. And this was kinematically a bit weird. So it's also a K-dwarf and has solar-like chemistry. So chemically, there's nothing too exciting going on here. But then when we look at it kinematically, it's kind of in between. So we can see, like on the tumor diagram, which I just separated here for thin disk, thick disk, and Hercules, that it's lying kind of outside of the thin disk. So nothing too exciting here. It looks like it's lying in the thick disk, but then if we also add the Hercules stream, it is also lying right at the edge of the Hercules stream. And just based on kinematic probabilities, the majority of it seems to belong to the Hercules stream and has quite a high offset in U velocity. So that was interesting. And also because we do have solar-like chemistry, we can't really tell what it belongs to because the Hercules stream doesn't seem to vary much in chemistry. So it was quite interesting to follow this one up. So again, we got TESS, KOPS, and HARPS data. We found 2 planets. I'm just showing planet B here because that's the inner USP super-Earth. But we also then managed to obtain a precise planetary radius and a 3 sigma mass detection. And with this, we could also get a density. So we were now putting this onto Vardan's plot, which I showed before. I also added 2 more metal poor targets, which were discovered since Vardan's paper. And we find that it's kind of lying in the regime of the super-Mercuries. However, it has quite high uncertainties, so it could also bridge the gap between the super-Mercuries and super-Earths, which could also impose new questions on theory and the formation of these clusters, whether they actually exist or not. And if it is a super-Mercury, it's lying compared to the other ones at quite a low F-iron star. So it's still kind of solar-like, but slightly more poor, slightly more metal poor than at least the other super-Mercuries. And also kinematically, it seems to be the only one that has a very low thin disk probability. So we are not sure what's going on here. It would be great to get more data to actually constrain the density better as well and see where exactly it lies, but also to find more systems that kind of challenge this plot and either bridge the gap or lie on sides where we don't expect them to lie. So with the machine learning, we also identified furthermore targets, which we are right now also following up. So this is one where right now we have a program running on Harps North. And this is also kind of challenging the plot I've shown before. So very far on the left-hand side, I'm showing again Vardan's plot. But this target has a very low F iron star. So it's a very metal-poor alpha-enhanced target. It is like the purple vertical line, since we don't have the mass yet, as we are just observing it. We don't know where it lies in density. If there's a linear trend, it should be very low in density, but we have to measure it to see. It is quite exciting, though, because of this. We can also see it's quite nicely lying in cluster 2, my thick disk cluster, in the middle, and then also on the tumor diagram. Kinematically, it lies very far out. Again, it is the black star. It lies very far out in the thick disk. And here I'm also just showing the known and confirmed planets that are below, I think, 4 Earth radii, and then have precise mass measurements. And we can see, based on the color coding of the metallicity, that this target is very metal poor. So it will be quite exciting to actually get the mass and see what's going on there. And with this, I'm just going to leave you with my conclusion that we have a lack of planets orbiting metal poor stars. We're using machine learning to trying to identify these chemical clusters and following up more of these targets to explore trends. And we have ongoing observations, and we'll see if we can confirm these trends in the future. Thanks a lot.
Awesome. Thank you so much. Do we have questions for Yoshi? Okay. I see a question over there. Yes.
Great talk. Thank you. Madeline Broom, UC Santa Cruz. Does your machine learning allow you to identify stellar streams or moving groups?
So we're looking into this right now. So we are right now mainly just targeting the difference between thick disk and thin disk. So for the streams and also moving groups, we are more just relying on the kinematics instead of just going based on the chemistry.
Okay, other questions? Yes, over there. Please remember to state your name and affiliation.
Drew Oysterman at McMaster University. Can you talk a little bit about how you calculate the FE over H and the alpha enhancement? Is that something you do, or is that something Apogee does? And do you know like how they do it, or what different what different alpha elements go into calculating that?
So I'm mainly just like following what Apogee is doing there. So there's not really anything I'm doing in my computations. Yeah. I think it's actually on their website which elements they're using. And I have it in my code, I can look it up, but I don't know off the top of my head which ones I included and which ones I didn't. Yeah.
Okay, do we have one more question? Over there, please. Yeah.
Bennett Skinner, other McMaster University. Are you concerned at all about introducing any bias by it not being a blind survey, and you're kind of specifically trying to look for things that you're most confident are in some kinematic group?
Sorry, how did you mean?
Like, if you want to characterize a star in the thick disk,
Yeah.
you want to be like confident it's actually in the thick disk. So is it possible that the objects which you're extremely confident are in the thick disk aren't actually all that representative of the population as a whole?
So I think we are trying to mainly just like target the ones where we have chemistry and kinematics, the thick disk, but we have some also overlap targets. So it's sometimes just like, oh, just kinematically, this is interesting because it might be easier to identify. So it's sometimes just a mix of confidence, or if it's also just like, if a target's already kinematically interesting, we'll just go after it as well.
Okay, I think I don't see any immediate questions, so let's thank the speaker again. Yeah, and also remember, of course, throughout the day, when you have a question that cannot be asked during the time of the Q&A, then please go and speak to the speaker afterwards in the breaks and ask them their questions on Discord. Our next speaker will be Elena Zaharia on the influence of extrusive magmatism on rocky exoplanet tectonics. Please take it away. Oh, that downwards.
Can you hear me? Yeah? Yeah. Hi, everyone. I'm Elena. Today I'm going to talk about how planetary mass and magmatism can influence the tectonic regimes on exoplanets, rocky exoplanets. Work done at UCL during my PhD. So we've been seeing these plots for several times now. So I'm not going to go into details, but I want to still mention how rocky exoplanets have sizes up to 2 Earth radii and up to 2 Earth masses, and bulk densities similar to Earth's density. Some of them might harbor plate tectonics. However, we are not able to observe this. So we use numerical modeling to simulate the interior and the evolution to find out more about this. In our solar system, we have two confirmed tectonics, mobile lid on Earth and stagnant lid on, for example, Mars. And here you can see a cartoon, and on the left and on the right, a snapshot of my models. Mobile lid is defined by a lithosphere that breaks into multiple plates that sink into the mantle at subduction zones and form a spreading centers, plates that interact with each other boundaries, while a planet in a stagnant lid regime is defined by a thick rigid lid that doesn't subduct or doesn't have mid-ocean ridges, but it has limited to no surface motion. We know about this, but with the help of numerical modeling, we also recognized more tectonic regimes like episodic lid. And episodic is defined by periods alternating between stagnant and episodic and mobile. So we have a stagnant lid period where the crust becomes thicker and thicker, and becomes gravitationally unstable, and then it breaks and materials sink into the mantle. We have these tectonic regimes, but we don't know the conditions under which they form. So in the past, there have been, for example, work on how mass could influence the tectonic mode a planet is in. However, past research have come with different conclusions. Some came with the conclusion that with planet mass increase, there's a likelihood of plate tectonics, but stagnant lid, in other research, stagnant lid is present in larger planets. So the conclusion was not defined. So also, I would like to mention that this model did not have melt, cluster production, or in extrinsic magmatism in the model. So this leads us to the goal of my project, to include these factors and to investigate the planetary mass and the effect of planetary mass on plate tectonics and other modes. So we do this by using a mantle convention called STAG-YY to generate models that are sub and super Earths with the sizes from 0.75 up to 2 Earth masses. Key parameters that we investigate are planet mass, surface yield stress, and extrinsic magmatism. And the surface yield stress is the critical point of deformation, a permanent lithospheric deformation. So I'd also like to mention how melt is working in our model. So when the material in the mantle, the temperature of the material in the mantle reaches, passes the solid deuce temperature, then the material will melt, and then the melt will be moved to the surface and extruded there. And then at the surface, it would instantaneously cool to the surface temperature, which we have set to 300 Kelvin, and will form a new crust, and then the material left behind will be depleted. To analyze these models, we use two parameters, plateness mobility, and plateness is defined as the degree to which the surface deformation is localized, and a plateness of 1 would show that deformation occurs at small zones like plate boundaries, and a plateness of 0, which shows that deformations occurring across a larger area. So in these plots, we have an example of mobile lead with plateness high, and an example of stagnant lead with plateness close to 0. The mobility shows how the surface moves in comparison to the mantle, and you again have an example of mobile lead showing a high mobility, but for a stagnant lead, the mobility is very close to 0. We are also using another parameter called plate activity that shows the time fraction during which a planet is tectonically active. And for a planet that is in a mobile regime, the plate activity is close to 1. And a planet that is in a stagnant regime indicates that the plate activity is 0. We simulated 44 models, and we mapped them into this diagram. And we can see on the x-axis the square root of surface yield stress with values for 5 to 250. And on the y-axis, we have the planetary mass in relation to Earth mass with values from 0 to 75 up to 2 Earth masses. And the color map shows plate activity. I would like to mention that the gray color is from 0 to 0.01. So for low surface yield stress, we have high plate activity. For high surface yield stress, we have low plate activity. And for intermediate surface yield stress, we have medium to low plate activity. So if we want to put this into a tectonic diagram, it would look like this, with low surface yield stress, with mobile lead in a low surface yield stress, stagnant lead in a heat pipe mode at high surface yield stress, and with the intermediate surface yield stress showing episodically. However, at the regime boundary, we have some models that show transitional behavior. So I'm gonna go into, I will show a few examples of this. This is a mobile lead example where you can see in the video, there is material subducting and then material rising with the help of plumes. In the plateness mobility cases plots, you can see how plateness is close to 1 and mobility is very high. So it's corresponding, values corresponding to a mobile lead mode. Here you can see a stagnant lead example with the crust forming and becoming thicker and thicker, but no subduction occurring. So here in the plateness mobility cases, you can see that the values are very low, close to 0. And here I'm showing an episodic lead example where the material is where there are two phases, stagnant phase and active phase. So in the stagnant phase, the crust becomes thicker and thicker. In the active phase, you can see material sinking to the mantle. And this can also be shown in the plateness mobility plots, where we have low plateness mobility for stagnant phases and peaks of activity, showing activity in the model. How am I doing with the time? Okay, thank you. So here we have a model that is at 40 years stress, which is at the regime boundary. And then in the video, we can see that it starts with a stagnant period, but it's followed by mobile period. So this behavior, I was able to see both at 40 and at 140 surface yield stress. So we call this a transitional behavior, moving from stagnant to mobile. To conclude, so the models I'm showing with 100% extrusion indicates that mobility is present in low surface yield stress, episodically is present at intermediate surface yield stress, and then stagnanite is present at high surface yield stress, with models that are located at regime boundaries that show transitional behavior between tectonic regimes. And I'll leave you with my future steps. Yeah. Thank you.
Awesome. Thank you so much. Do we have questions? Okay, yes, please. Over there on the right. Yeah.
Hi, thank you for the nice talk. I'm Chandan Sahu from Penn State. Do you have any idea of how episodic lit starts or what drives it from, say, starting from mobile lit or stagnant lit? And since we have some theories about Venus being any of those or being in the episodes, can you comment on that?
In our models, the mental stresses become higher than the stresses at the surface. So this will break the crust. In reality, I think this is still a subject that is still under, a lot of development. It's the same as how plate tectonics started. They're kind of related, so we don't really know the answer of that. Also, Venus, I think, is also considered to have, like, people think that it's in the past have been in episodically, but some other more recent studies show that it's in a plutonic squishy lead regime, a new tectonic regime that was like published a few years ago. So many people are also studying Venus now.
Okay, before that, we have an online question, and then you afterwards.
So, can you speak a bit about your choice of interior compositions?
My structure, or
Choice of interior compositions. Choice of interior compositions.
using a basalt and Hasburgite composition, I think. Oh, sorry.
Do you know with the question?
Yeah, so for the composition, I'm using 10 members, basalt and Hasburgite, with basalt being pure pyroxene garnet and Hasburgite being a mix of olivine and pyroxene. I have also phase transitions and a Newtonian rheology. I'm not sure, yeah.
Yeah, no, I think
Yeah,
that's okay.
yeah.
Thank you so much. And we have one last question here.
Hi, Xuecheng Yang from ETH. So if I remember correctly, in Diogo's original paper where he proposed squishy lead, he set the extrusion rate to a relatively small value, but here you use like 100% extrusion rate,
Yes.
but you still see squishy lead. So
I don't
what's the
see
big deal?
squishy lead in my models.
Why is that? Can you elaborate?
Oh, why is that? Well, we need, according to the authors that published the squishy, we need intrusion to see these squishy lead models. While in my models, I have 100% extrusion, so all the melt goes into the surface. I don't have any melt intruded into the crust to form these ponds of melt and weakens the material under. So I wouldn't expect to see in my models this plutonic squishy lead. But if I include intrusion, extrusion, I might. This is the next step I'm doing, so yeah.
Okay, awesome. Let's thank our speaker again. Thank you. Before we start with the next talk, when you stand up on the side, can you try that your seat doesn't tuck to this thing, which sometimes a bit hard to understand here then. Our next speaker will now be Hannah Sanderson on magnetic dynamos in planetesimals.
Okay, yeah, that works. Oh, down. Okay, cool. All right. Hi everyone, so I'm Hannah and I'm a postdoctoral fellow at the University of Oslo. But today I'm going to be presenting some work I just did towards the end of my PhD about how we can use magnetic field generation to understand differences between the inner and outer solar system. So the main question motivating this talk is how different were inner and outer solar system bodies. As we've heard earlier in the week, we know there's an isotopic difference between these bodies. We have a clear population in the inner solar system and a population in the outer solar system. But something we want to understand, because these bodies were the building blocks of our planets, was how different were they? Apart from their isotopic composition, did they have different core sizes, different water contents, and to what extent can they trace their formation conditions? Or does planetesimal evolution override any fingerprints of their initial conditions? And as well as caring about this because this is the stuff that eventually ended up in the rocky planets, we also care because these differences could also trace the triggers for planetesimal formation and help us understand how the planetary building process actually begins. So as Dan Veer explained really nicely in his talk on Tuesday, there are kind of two possible hypotheses for how planetesimals start to form. So for the planetesimals to start to form, we need them to, there's going to be a buildup of density of material. And one place we think this happens is at ice lines. So in one hypothesis, we have the water ice line that starts in the inner solar system and then migrates towards the outer solar system and then back in again as the disk evolves. And in this scenario, we would see three key things about our planetesimals. So we would see the planetesimals forming sequentially, first in the inner solar system and then in the outer solar system as the snowline migrates. But we would see them forming with very similar water content and similar oxidation states because they're always forming at this water ice snowline. In the other hypothesis, where we have planetesimal formation at distinct snowlines, so the inner solar system ones form just outside the silicate sublimation line, and the outer solar system ones form at the water ice snowline, we can have the same three observables, but we would see different things. So in this scenario, we would see planetesimals forming everywhere at the same time because they can form, they don't need the snowline to move around. But we'd see them forming with very different water contents and oxidation states. The inner solar system ones would be dry and they'd be more reduced. And there are ways you can measure this directly by looking at the water contents of meteorites, or as Daman explained, having a look at the oxidation states of iron meteorites. But those measurements are very difficult to do. So what I'm trying to explore today is, could magnetic field generation in planetesimals be another new tool for exploring these differences between these populations? So the reason this might work is because of the precise criteria required to generate a dynamo. So to generate a dynamo in a rocky planetesimal, we need three key things. We need to have a metallic core, so this kind of electrically conductive portion of the planetesimal. We need to have a this core to be at least partially molten so we can have flow. And then we need to drive the flow. And then it's this flow of electrically conductive fluid that in turn creates an electric current, which then makes the magnetic field. So if I say the word dynamo or magnetic field generation kind of in this talk, they're kind of referring to this concept. And this flow can be driven in two key ways in these bodies. They can either be driven by thermal convection, so basically when the core is rapidly cooling, you get temperature-induced density differences, or they can be driven by compositional convection. So when the core begins to solidify, we reject light elements from the solid phase into the liquid phase, generating a density contrast and driving convection. So I have a code that basically models a planetesimal's thermal evolution and its magnetic field generation, in which we can vary a wide range of planetesimal parameters. So I can use this to predict thermal and magnetic histories of different bodies, and then compare them to the meteorite magnetic record. So to investigate this question of this difference between the inner and outer solar system, I'm going to invoke two different planetesimal end members. Dry planetesimals that have basically no water in them at all and form a kind of a more reducing environment, so have slightly larger cores, and then wet planetesimals. So when I say wet planetesimals, I mean planetesimals that would have accreted with a substantial amount of water ice. And as they heated up through the decay of radiogenics, most of that water ice would have melted and been lost to space. But a small amount might have been retained in nominally anhydrous minerals. And this upper bound that I'm using here is based on our measurements of meteorites of how much water they could possibly contain in these minerals. Now, this water could lead to three key differences between these planetesimals. So the water is going to lower the mantle solidus and also make the mantle less viscous. And it's also going to lead to smaller core sizes because these bodies are forming in a more oxidizing environment. So these three key differences go into my planetesimal magnetic field generation model. So what do the results look like? So on this panel, we've got an upper and a lower panel. The lower panel is for the wet planetesimals, and the upper panel is for the dry planetesimals. And then the horizontal axis is time since the solar system formed. And the length of the bar is telling you when the magnetic field is being generated, and then the color is showing you how strong that field is. And at the moment, I'm just showing us results for 500-kilometer radius bodies. So immediately from looking at this plot, you can see two key differences. So the wet bodies are consistently producing shorter-lived magnetic fields. We're only getting fields to about 200 million years after the solar system formed, compared to about 550 million years. And this is because of that water that's present in the mantle lowering the mantle solidus. And this means that the mantle starts at a much cooler temperature when you have differentiation. And so there's less cooling required from that peak temperature to reach the core liquidus. And this means core solidification begins earlier and also ends earlier. And if you remember, once we have a solid core, we can't have a magnetic field anymore, and so that turns off dynamo generation. The other key difference you can see is that the dry bodies produce much stronger fields than the wet ones. And this is because of the core size. So magnetic field strength falls off as a 1 on r cubed law. So because in the wet bodies, there's a larger distance from the core mantle boundary to the surface, your field strengths at the surface are much weaker. So at the moment, it's looking promising. It looks like there's some big differences between these bodies. But we also need to know how this varies with body size, because size very strongly affects cooling rate. And if size has a bigger impact than wet versus dry, then if we pick up a sample and we don't know what size body it came from, then this contrast is kind of useless. So now I'm showing you the results for the same comparison, but for radii from 100 to 500 kilometer radius. And again, you can see that for any given size, this same trend holds true. The wet bodies have shorter lived and weaker dynamos. But we can also see that if we kind of pick a time, maybe about 50 million years after CAIs, and picked up just a meteorite we didn't know what size body it came from, the wet bodies are always going to have weaker fields irrespective of their size. They're kind of 5 microtesla or less, while the strong bodies have magnetic field strength kind of 10 microtesla or above. So it suggests if we can get a good paleointensity, so a magnetic field strength out of our rocks, we have a good way of testing whether we think the object looked more like the dry end member or more like the wet end member. So with that in mind, let's look at some data. So now you've got the same plot on the top, but I've added a third panel. And this third panel is showing magnetic field measurements from meteorites. So things that are on the same horizontal line have come from one meteorite parent body, so they're a group. That's one planetesimal. But we've got multiple meteorites from that planetesimal that recorded a field at different times. And so we've got 4 different bodies there. And they're all from the inner solar system. And then they've color-coded them by the same color scheme I used for the plots above. The 2 white points correspond to null paleointensities, which you want to know more about, you can ask me later. But we can see that all the other points, which are kind of yellow and green, have similar field strengths to the dry end member rather than the wet. And again, they're in this key time range more than 50 million years after CAIs, we have this biggest contrast. And so this suggests that the inner solar system meteorites look closest to the dry end member. And this can kind of mean one of 2 things. Either it means these bodies formed very dry, so there was never any water in them, or they degassed very efficiently during their differentiation process. So even if there was water, we're not seeing a trace of it in their subsequent structure and evolution. Now, to test this, what we really need are outer solar system meteorites to be measured, which we haven't done yet in this right time range. So what would we see if we measured these outer solar system meteorites? So if we measured an outer solar system meteorite in this key time range, and it did have a magnetic field, that would be really interesting, because it would tell us that those bodies also looked similar to these dry end members. And since we think that outer solar system bodies almost certainly formed at or beyond the waterized snow line with some water, this would imply that degassing was very efficient and prevalent throughout the solar system, because these outer solar system bodies have essentially erased any trace of the water that they formed with. On the other hand, if they have very weak fields, they'll look more like this wet planetesimal end member. And this would suggest there was a contrast in the water contents between the inner and outer solar system, because there's no reason why the inner solar system bodies would be able to lose their water very efficiently, while the outer solar system ones could hold on to it, because they're going to have similar thermal evolutions. So therefore, this must mean there must have been a difference to begin with in their water contents. And this could also then lead to kind of possible formation of different condensation lines hypothesis. So the key message is we need to go and measure some of these meteorites. And there are targets that we're looking at that will hopefully be measured in the next few years. So in conclusion, I hope I've convinced you that planetesimal magnetic field generation could be a new tool for probing the differences between the inner and outer solar system, because we have this contrast between the wet bodies that have shorter lived and weaker fields than those in the dry case. And we basically need to go and measure some meteorites. And if the paper is kind of, this is almost ready to be submitted, but not quite. But if you want to know more about the methods I'm using, the model that I'm using is already published and also available on GitHub, so you can have a look at it and come ask me questions. And also a quick plug, some of you might be confused, I've kind of been wearing a magma ocean hat this week, and that's because my postdoc is going to be on metal silicate separation magma oceans. So if you want to talk to me about that, also please come and chat to me later. Thanks.
Awesome. Thank you so much for this very nice talk. Questions? Yes, let's start there in the middle.
Hi, Hannah. Great talk.
David Rice, University of Wisconsin-Madison. Wondering about radiogenic heating, what your assumptions are, and does it, I assume it depends a lot on that. Is there different radiogenic heating in the inner and outer disk, and is there different depending on how wet a body is? Would that affect that at all?
So that's a good question. For aluminium-26, which is the primary heat source for these bodies, I think it's been quite clearly shown that there's the same amount everywhere in the inner and outer solar system. Radiogenic iron 60, which goes into the core, could be different between the inner and outer solar system. It's still debated, but that has is only going to affect the core at very early times. I showed one of my early papers. So for this kind of later contrast that we're seeing here, a possible difference in that radiogenic isn't going to make a difference. When you accrete with water, you initially are going to have a lower concentration of aluminium-26 in your body because you've got water in there, which isn't a carrier, mixed in with your silicates. But that process of heating up and differentiating and losing that water happens so early that it's not having an effect on the long-term evolution. But what I did to kind of account for that problem is I looked at the effects of different differentiation times. So assuming that these bodies that have more water maybe differentiate more slowly because they have a lower concentration of aluminium-26. And you can see that it makes no difference. So it doesn't matter.
Yeah, over here. Helen Williams, second row.
Thanks very much. I'm Helen Williams, Cambridge. So really interesting talk. How do the water contents that you might infer from your magnetic measurements, how do they link with, say, the more volatile siderophile element abundances or oxygen fugacities inferred for these different parent bodies?
So I've not looked at any other moderately volatile elements, something I could think about. But it's harder to know how they're going to affect like the rheology and the things that are going to affect the thermal evolution, which I haven't really thought about them yet. Whereas kind of the effect of water on viscosity and solidus is better documented. In terms of oxygen fugacity, there are like studies like Dowman try and link kind of the core sizes to oxygen fugacity. So I did try and think about that a bit. But again, it's kind of hard to do because it depends on what your assumptions are about how the cores are fractionally crystallizing. So at the moment, I'm just stuck with more oxidized, more reduced, rather than trying to put a hard and fast number on it. Yeah, hope you answered the question.
Another question? Then I have one more quick last question. You said you could, so this depends on how quickly you lose the water. When you say quickly, how quickly do you mean? How quickly would you need to lose the water in order to get essentially the data points from the inner solar system you have to match with your models?
So when I say how quickly, I guess I'm thinking about that time lag between accretion and differentiation. But we know from the iron meteorites and the hafnium tungsten and then we kind of know that range of when they differentiated. So irrespective of how early they formed before that, by this time after CIs, they must have formed differentiated bodies. So that's the kind of input range I've used here is just the input range of the isotope record. So yeah.
Okay, awesome. Let's thank our speaker again. All right, so the next speaker will be Maxim Balmer on, Mission Impossible 2, I guess. Yeah.
Yeah, I'm trying the impossible and giving 2 talks in 10 minutes. So let's see if it works. Press down, okay. Yes, the first project is by a postdoc in Hong Kong, Chen-Yang Liu, and it's a bit for follow-up on what Elena just said. This is published in Nature Communications, so I'm gonna go quickly through it. And so Elena has been presenting these 3 different regimes: mobile lid, episodic lid, and stagnant lid. So mobile lid, a little bit like plate tectonics. Previous work has shown, that there's an effect called hysteresis, which is kind of annoying, so that there's a quite big range in the parameter space, depending which cross-section of the parameter space you used, where the results are basically uncertain. So for the same parameters, for the exact same parameters, tiny difference in the initial condition or just random noise, you get a different answer. So you get a stagnant lid or a mobile lid. So that makes the models in this range unpredictive, which is a problem for exoplanetary science in particular, because we don't have data to ground truth these models. We have to rely on these predictive forward models. So that's what I just said. And then it gets even more complicated. So there's been a question previously, there are more tectonic regimes. There's this plutonic squishy lid regime, and there's a whole zoo of regimes, depending on how exactly you draw the boundaries between the regimes. And as has been already mentioned by Elena in her answer to one of the questions, the plutonic squishy lid, for example, is sustained by intrusive magnetism. So from geologic evidence on Earth, we think that about 80 or even 90% of mantle melting would intrude into the lithosphere or at the base of the lithosphere, and that changes the dynamics because it heats up the lithosphere. So that's an effect that Chen Yang has been taken into account, and then he ran similar types of models. He did similar types of analysis. So for example, analyzing mobility and plateness, which Elena also did. And then he found a new regime, which was not described before, the episodic squishy lid regime, which is basically just alternating between the plutonic squishy lid, which, as I mentioned, was already described by Diogo Lourenço, and then the mobile lid. So it's an episodic regime, but it doesn't episode between stagnant and mobile, but between mobile and plutonic squishy. And it's smack in the middle here, smack in the middle here of the parameter space. So we could then map out all these regimes, put them into context with each other. Actually, we didn't have any issues with hysteresis. I'm going to come back to that later. So what we varied primarily three different, so in the main text, three different parameters, but two of them are co-varied. These are thermal parameters. So at the top, these are early hot planets, and that moving down, these are cold, old planets, cold and old. And then on the horizontal axis, we have the surface yield stress, which is the effective strength of the lithosphere. So it's one of these notorious parameters. We don't really know which number to put, and we always vary it in basically every geodynamic modeling study, because laboratory measurements provide a value that is somewhere over here. But the effective strength of plate boundaries on Earth, we know is much lower. Otherwise, we wouldn't get a mobile lid, we wouldn't get plate tectonics. And it has something to do with upscaling time and space. There are many small effects that have to be taken into account, and it's effectively the strength of the interface of the fault at the of the subduction zone that controls this. So it's a bit complicated, and we vary it, but we find a lot of different parameters, different regimes, and we analyze them and we characterize them. And then, of course, we're wondering about the path of Earth through this regime diagram. So in the beginning, Earth might have been, well, quite hot. And then based on these complex rheological mechanisms that I just mentioned in the lithosphere, so for example, the dynamical frictional instabilities at the subduction interface, and also something that is called damage rheology, which is a grain size dependent mechanism in the deeper part of the lithosphere. We would expect that with cooling, the effective yield stress actually goes down, so that the plastic strength of the lithosphere goes down. And that would imply that the early Earth would have evolved through, for example, an episodic squishy lid regime. And then in the paper, we compared that with geological evidence, and we argue that that this is reasonable. And then towards the mobile lid for Earth. For Venus, for example, Venus was always hot. So a path more like this, these two paths are more likely, and this path is maybe less likely. So lithosphere was always strong, and therefore, in the present day, this models predict that it would be in the episodic squishy lid or in the plutonic squishy lid, and that has been also argued to be consistent with the radar images and the surface geology, so to say, or structural tectonics of Venus. So we did some additional analysis to address hysteresis, and we can rule out hysteresis in these models. So here you have to go through the supplementary of the paper. I'm not going to go through the details, but we don't see any evidence for hysteresis. So this is good news. The models are more predictive. We account this lack of hysteresis The models, yeah, are more robust. The regime map is more robust than what we would have expected in the beginning. We account this lack of this annoying hysteresis effect because of the effects of intrusive magnetism, when we compare it to other studies which are already out there. So why am I talking about all these regimes? Why do you care about these regimes? Why did Elena talk about all these regimes for the whole time? It's because plate tectonics obviously sustains a weathering cycle by building up mountains quite efficiently, and then also it buries, so it's ingassing of the planet buries carbon and water back into the huge mantle reservoir. Okay, let's move on to something completely different. The next part of the talk is about long-lived mantle stratification in rocky planets as a function of size. So this is work by my postdoc at UCL, Antonio Manjon Cabeza Córdoba, and also collaborating with Ollie, who you know, I'm sure, and who is around. And this is about the magma ocean, as Charles Edouard mentioned yesterday. If you crystallize the magma ocean, so this is the very simplistic view of bottom-up crystallization, then you enrich the magma ocean because you remove magnesium-rich crystals. And I think the movie is not working, but this is supposed to be showing that while the crystallization front is moving, you would also already have mantle convection starting, and some of these then iron-rich cumulates, which would be in these bluish colors, would sink to the bottom, but they would not be efficiently mixed because they are so iron-enriched in this fractional crystallization model that they cannot be entrained by mantle convection. For Earth, this is inconsistent with seismic observations or with any geophysical observations. We do see some anomalies at the base of the mantle, but they are very subtle if you compare that to what these fractional crystallizations models predict. So for Earth, there must have been some mechanism that would have remixed these cumulates, or maybe the cumulates never reached these very high iron numbers, which you would expect for fractional crystallization. For Mars, the same models have been used, and for Mars, they work. For Mars, you would also predict a basal layer, a basal silicate layer, highly iron-rich layer, and it's there. We have seismic evidence for this. And it's apparently even molten and maybe makes an early magnetic field. So as I mentioned, convection is already going on in the mantle while the magma crystallization front is progressing. So what you get, you not only get crystallization, but so this movie should be working, while you not only get crystallization in these above these downwellings where you get dynamic topography lows, but you also get melting above these upwellings, so above these plumes. So there is an interchange between the two reservoirs. So the magma ocean will not just get more and more and more enriched, like in the cartoon in the beginning, but it will be buffered at some moderate iron enrichment, depending on some parameters. And this topography, which you can see here with the naked eye, is actually huge. So this is much higher than the dynamic topography you are familiar with at the Earth's surface in the present day. And so interestingly, we can reproduce this dichotomy between Mars and Earth. So this is the maximum iron number that the buffered magma ocean attains. And for Earth, it can be low as long as the timescale of magma ocean crystallization is above 1 million years or a few million years. And for Mars, is always high. You will always get this very highly iron-rich layer. And then this should be forming a dense basal layer, maybe dense basal magma ocean. Whereas for Earth, mixing during overturn or subsequent entrainment of this moderately enriched layer is feasible. And this is the last slide. So feasible as long as you have these moderate, well, relatively long, but still realistic timescales of magma ocean crystallization. So the last slide now is the implications for exoplanets of the second part of the talk. So basically the main effect is planet size. Here for Mars, it's also a little bit the composition, but for small planets, we have a long-term stable basal, we predict a long-term stable basal enriched layer. And for larger Earth-like planets, well-mixed mantle. And that's the conclusion slide. Well, check out the paper and the YouTube if this was too fast for you. Mission accomplished.
Thank you so much. Kudos for making it roughly in time. Well done. Questions for Maxim? Yeah, at the top right there, please. Oh,
Bennett Skinner, McMaster University. Could you go back one slide?
Yeah, sure.
Yeah, so here you have the kind of parameter space you looked at, and then in the dashed lines on either end, you're kind of trying to extrapolate out of the regime.
Yeah.
Are you
from the parameters that we can study? Yeah.
Yeah. Are you 100% confident that it's monotonic like this?
The extrapolation, if we're 100% confident, of course not. No, this is just.
So
just
what number between 0 and 100% are you?
This is a parameterized approach. I didn't really say that. So this is I showed the model, but this results actually coming from a parameterized model, a 0D model. I'm not sure I really got the question, but we just didn't run cases here for very small planets, but very small planets should be definitely very iron enriched, even more than Mars. So it's going to be a stable layer. And then maybe the thickness of the layer would vary. And here we are not sure what will happen. Because, yeah, I guess we could run more models, but this paper is mostly designed to be about the Earth-Mars dichotomy, and then the exoplanet implication is a bit of an afterthought. But in principle, we could run more models because these are very cheap. These are parameterized convection models.
Okay, here in the front, please.
Hi. Quinn, Technical University of Denmark. You showed this nice map of like a zoo of tectonic regimes and everything. And I was wondering, as someone who comes from the exoplanets angle, we have a lot of bare rocks that we're finding. Are there any surface signatures that we could find that could help map these planets onto this zoo? Are there like specific observational signatures of the surface that we should be looking for?
Well, I think for exoplanets, so for solar system planets, we can look for tectonic features on the surface, topography, things like that, maybe even magnetic field. But for exoplanets, I think our best hope is the interior atmosphere interaction, that we would have to look for indirect signals of plate tectonics, for example, if we can establish that the atmospheres for mobile lid plate tectonics are different than from a stagnant lid or an squishy lid. So we would have to couple the model with an atmosphere evolution model, I think.
Is there one last question, maybe? Yeah, here on the right, please.
Hi, Hannah Sanderson, University of Oslo. I was just wondering if you could expand a bit more on why you're seeing this trend in the buffered iron number with size.
So that's again the other part of the talk. There are, so it's mostly a function of size because the Rayleigh number increases with the mantle thickness, and I'm not sure in which direction I go, but the Rayleigh number increases with mantle thickness, and the Rayleigh number, you get a higher convective figure. So you get more vigorous convection, more strong, so more vigorous remelting, and therefore more efficient buffering. Or you're basically buffering at an earlier stage of the progression of the crystallization front. And also if you have a longer time scale of the magma ocean, then because the progression is slower with respect to that time scale, you're also buffering earlier, and that means you are reaching a lower iron number. So it would be also really interesting to couple this with an outgassing model, because obviously that is controlling the time scale of magma ocean crystallization.
Okay, let's thank Maxim again. And our next speaker will be Andy Buchan. on polluted white dwarfs and inferring geological constraints on exoplanetary systems from them. Please take it away.
Cool. All right. Yeah, okay. So hi everyone, I'm Andy Buckham from the University of Warwick. I'm here to talk to you today about polluted white dwarfs and why they turn out to be so useful for exoplanet science. So these have been mentioned earlier in the week, but I'll go over what these systems are to begin with. So this central object in the animation here is a white dwarf, essentially okay. Is that better? Okay, great. Okay, so white dwarfs. This central object here is essentially a dead star called a white dwarf. This one is shown with a disk, but that's not particularly important to us right now. What's more important is that we've got these objects that are falling into the white dwarf. And so these are probably remnants from the white dwarf's planetary system, probably small-ish bodies like asteroids or comets. And they've probably been perturbed in towards the white dwarf by some outer giant planet. So this is kind of the key point about these systems is that they're accreting material from their own exoplanetary systems. And when the material arrives at the white dwarf, we can detect it as metal pollution in the white dwarf's atmosphere. You might also hear the phrase metal enrichment. And by fitting model spectra to the metal lines that we detect, we can effectively measure the abundances of the different metals in the accreted material, including key metals such as iron, oxygen, calcium. And this is really valuable for us because it gives us a window into geology, or exogeology, you could say. And we can ask some really important questions. So, for example, for Earth, probably the two really key processes that shape its overall composition and first order structure are volatile depletion and core formation. And so we can start to ask the question of, do these processes also affect other planetary systems? So I'm going to briefly discuss these two processes and show you some examples of evidence for these processes in data from white dwarfs. So volatile depletion is something we've met already this week. The idea is that if we're forming bodies in a protoplanetary disk, then the closer you are to the central star, the higher the temperature is, and the harder it is to get volatiles to condense into the solids. And so this means that at different distances, at different temperatures, you form materials with different refractory and volatile content. So close in, you would expect material that's relatively high in refractory elements with high condensation temperatures like calcium, and you would be quite depleted in volatile elements like oxygen. So a highly volatile depleted body might be expected to have high calcium and low oxygen. And so here's an example of that in a white dwarf. So on this plot, we've got a variety of metals that we can model on the x-axis. And then on the y-axis, I'm showing the abundance of that metal relative to the hydrogen in the white dwarf's atmosphere, scaled to solar, and then put on a log scale, which is a lot of transformations, but really the point here is that a horizontal line on this plot would correspond to a solar-like composition, at least in terms of the metals. And so in this case, we have detections of calcium, magnesium, silicon, and oxygen, plus a bunch of upper bounds. And if I add a model fit to perhaps help guide the eye a bit, you can maybe see that relative to the magnesium and silicon, the oxygen is a bit depleted, the calcium is a bit high. And if you look at the calcium to oxygen ratio in particular, that's quite sort of pronounced. So this is very much in line with what we would expect for volatile depletion. And indeed, this model fit is one in which we are quite confidently invoking volatile depletion. So then the other process I mentioned is core formation. So the word core can be a bit tricky sometimes. It means different things to different people. In this context, I mean something like Earth's core as opposed to Earth's mantle. But that doesn't necessarily mean that we're just talking about planets. Smaller bodies can have this kind of structure as well. So large asteroids, for example, and as I've been finding out this week, Dutch cuisine as well. Something very similar, certainly partially molten. But the point here is that the core and the mantle have different compositions. So the core is very rich in iron and nickel and poor in calcium and magnesium, whereas the mantle is the opposite. So you can imagine that if we formed, let's say, a small asteroid with a core and a mantle, and perhaps it suffers a violent collision and breaks into fragments, some of those fragments might be more core-like and some would be mantle-like. And if you were to accrete preferentially some of the core-like fragments onto a white dwarf, the expected signature would be, you would see high iron and nickel. And so here's an example of that in a white dwarf. The plot has essentially the same meaning as before. And these two data points right at the top above everything else are iron and nickel. And so here again, we can find a nice fit. In this case, we're fitting this with a model that invokes a roughly 60-40 mixture of core and mantle material by moles. So these are really, I think, interesting and important results. They're showing us that these key processes for making Earth also happen in other planetary systems. But there is a caveat. Well, there's several, but I'm just going to focus on one here. The caveat is that the composition of material that we detect in the white dwarf atmosphere is not the same as the composition that was actually accreted. And that's because different metals, well, in fact, all the metals will sink through the white dwarf atmosphere towards the interior, but different metals will sink at different rates. So that's kind of what this animation is showing. The point is that something that sinks really quickly, like iron, for example, becomes apparently depleted in the white dwarf's atmosphere. And so that could potentially lead you to think that you're accreting iron-poor material, but actually that's nothing to do with the geology because it's just some nuisance factor that we kind of have to correct for. The problem is that to correct for this, you need to know something about the white dwarf atmospheric physics, and then things get really complicated. Because it turns out the white dwarfs are quite sophisticated in their own right, and there's a bunch of different model assumptions that you need to make, and it's not always clear what the best assumptions are in any given situation. So this introduces a very important systematic effect that really needed to be investigated. So in this work, we implemented different treatments of these white dwarf atmospheric physics that we need, making different assumptions about important processes, which I'm listing here. I'm not going to go into detail. And then we incorporated these different white dwarf assumptions into our Bayesian modeling code, which determines the most likely geological history of the accreted material. And we found 4 polluted white dwarfs where the conclusions are not sensitive to the white dwarf assumptions, and so in that sense are robust. And so 2 of them are the ones that I just showed you, actually. So we had this one on the left with volatile depletion, the one on the right with core-rich material, and 2 others which I'm not going to go into detail individually because they kind of repeat the same features here. So I guess the point here is that not so much that it's certainly not the first time, it's not the only white dwarfs where we've inferred these processes to be happening. But what is new and what is important, I think, is that this is the first time that we've really done this exercise of going through these really important systematics and checking that the interpretations are at least qualitatively consistent for any reasonable white dwarf assumptions. And so this should give us some confidence that we really can use polluted white dwarfs to say important things about geological processes, and that the systematics introduced by the white dwarf itself are not necessarily a problem. So this perhaps raises the question of what's special about these particular systems. And you might think, well, maybe it's because they're in a part of the white dwarf parameter space where the different assumptions are actually not doing very much, which is not the case, really. If anything, it's actually the opposite. Really what's happening is that we just have key metal abundance ratios that are sufficiently non-solar that you really can't avoid invoking certain processes in order to fit them. And that remains true even if you were to pick the white dwarf assumptions that would most compensate for that. Okay, well, that feels like enough. So yeah, I'll just very briefly summarize. So we can use white dwarfs to infer the composition and histories of exoplanetary systems. We are reliant on models of white dwarf atmospheres, and that could introduce systematics, and sometimes that could be still important, but it's not necessarily a problem. And so I've shown 4 counterexamples there. But if you want to read about this in more detail, feel free to follow that link. And yeah, if there's time, then I'm happy to try and take any questions. Thank you.
Thank you so much. Questions? Yes, we will start there. Yes, okay.
Hi, Andy. Really nice talk. Thanks. When you say that this object or that one of the accretions is 60% core, 40% mantle, how do you visualize that? Is it like some sample from the core mantle boundary or like different parts of the planet accreting in the same event?
Yes, so as in what are the physical processes that lead you to have a 60-40 mixture? Yes, so the model is actually, we're kind of agnostic to that. We just assume that there is some way that you get this preferential accretion of core-like material. There's different possibilities. So you could imagine that we're accreting collision fragments, and you happen to have accreted more core-like fragments than mantle-like fragments in the recent past, right? Because the material hangs around in the white dwarf atmosphere for some amount of time, so you don't necessarily need to accrete these simultaneously. Another possibility is that we could be seeing the remnants of like tidally shredded material. So if these rocky bodies are getting close to the white dwarf, they could be tidally disrupted, and then you could accrete core material and then mantle material preferentially at different times. In any individual case, it's very difficult to speculate on what the most likely cause is. But if you had enough, if you had a large enough sample size, you could actually disentangle those processes by looking at the kind of statistical trends. At the moment, we're limited by sample size on that, but in principle, that is something I would like to do in the future. So yeah.
Awesome. Yeah, here in the middle. Yeah.
Yeah, Will Meisner from Carnegie Science. Really interesting talk. I was just wondering, so you said you found 4 counterexamples. I was wondering, like, first, how many systems you tested and sort of what your threshold was for what was like robust against these systematics and what wasn't.
Yes. Okay. So yeah, you're asking like, what's the like how like what proportion of white dwarfs do we expect to have like robust interpretations? Yeah. So I didn't really put a number in it because it's a bit hard to tell based on what I've done. Right. So I was looking at a sample of about 45 white dwarfs. So nominally that suggests like 9%. But we were actually looking for white dwarfs where these assumptions would make a difference. So we're very biased against finding these white dwarfs that I'm showing here, right? So if anything, I would interpret that as like a lower bound. So it's somewhere north of 9%, but I don't know how far north. I can't really say based on this. We'd need to do like a more unbiased check. And then your other question was, what do you mean by confident here? So what I mean here by confident is that regardless of the white dwarf assumptions, the favored model, the Bayesian, so we're comparing the Bayesian evidence of different models, and we're in all these cases the Bayes factor is like really high, like in the hundreds of thousands, right? So this is like so high as to almost be meaningless. Essentially, the model is like saying it is absolutely certain that these processes have to be taking place, and I wouldn't read too much into the specific numbers because it gets to a point where the weak point is like the model itself, and I am not like 6 sigma confident in the model itself, right? But high enough that like it's sort of decisive in terms of like the Bayes factors. I've been to the context of this framework.
Okay, we can take one more question, but please both ask her and please keep it short, both of you.
Bennett Skinner, McMaster University. Hopefully this can be short. Can you elaborate a little bit on what the actual model differences are between your different atmospheres?
Sure, I can't quite see where you are, but between the different, between the different white dwarf atmospheres?
Yeah, you said there's some differences, like,
so
what are the differences a little more specifically?
Sorry?
Sorry, just what are the differences a little more specifically?
Yes, so the main ones are the extent of convective overshoot. This is when overshoot continues beyond the formally convective region of the white dwarf, but it's not clear exactly how that should be parameterized. We also have differences in whether you invoke thermal halide mixing. So this is a key process that is an instability that can develop when you have an inverted mean molecular weight gradient, as would be the case if you're accreting material onto a white dwarf. I suspect I don't have time to go into detail.
No,
Feel free.
please have a longer discussion later on in the break.
Cool.
Let's thank our speaker again. Okay, our last talk of the session is by Jamie Williams, and we'll stay on white dwarfs, and so we look forward to that talk.
Hi everyone, I'm Jamie from the University of Warwick. I'm a final year PhD student, and I'll also be talking about things accreting onto white dwarfs. So although Andy's just gone over it, I'll do a brief introduction again. So a white dwarf itself is the endpoint of stellar evolution. It's the bare core of a star, which has exhausted all of its hydrogen fuel, and the outer envelope has been ejected. They are very dense objects, about 0.6 solar masses, within an object about the size of the Earth. Because they are so dense, they have a very high surface gravity, which means that all metals heavier than helium will fall towards the core, which leaves behind a pure hydrogen or helium atmosphere. Except that's what we expect, but we see a lot of white dwarfs with enrichment in their atmospheres from heavy metals, and this is caused by planetesimals, which are the survived post-main sequence evolution. They are subsequently scattered towards the white dwarf. They fall within the Roche radius, and they are torn apart, forming an accretion disk, which gradually accretes onto the white dwarf, which we can detect via metal enrichment. Then if we measure the abundances of metals in the atmosphere, we can therefore determine the parent body composition. So yeah, today I'll be talking about the Hubble Space Telescope survey of hot white dwarfs. So we primarily use the cosmic origin spectrograph, which is a medium resolution spectrograph about boson power of 20,000, which is in the far ultraviolet. So we focus on hot white dwarfs above about 12,000 Kelvin. This is for two key reasons. One is that they have very short shrinking timescales on the order of days or years, which when compared to the accretion timescales of millions of years, we can be sure that accretion must be ongoing. Another reason is that we have the full complement of metals in these white dwarfs from like siderophile, lithophile, and volatile elements. So yeah, we've observed about 450 white dwarfs in a snapshot surveys, as well as dedicated programs, and about half of these show evidence of enrichment. So about half are either currently accreting planetesimals or have recently. And then about 20% of these, so about 45 to 50, have multiple metals. So with these, we can perform compositional analysis. So how we measure the abundances. So this is an example of one of the spectra we obtained. So as you can see here, there's a lot of metal lines. If this white dwarf was not accreted, we would just expect to see a flat spectrum there. But here in the cloud here, we can see a lot of lines from silicon and iron, as well as some from the ISM from nitrogen, which we mask out. So we use model atmospheres to generate a synthetic spectrum, and then we fit this synthetic spectrum to the white dwarf using a chi-squared minimization approach to determine the number of evidences of all of the metals. So I don't think I have time to go through all like 50 white dwarfs that we have that we can perform compositional analysis for. So I'll talk about two key results. So the first is core-rich planetesimals. So core-rich planetesimals are formed through differentiation. So the material combines into a planetesimal, which undergoes melting either due to gravitational potential energy or short-lived radioactive isotopes, which forms a differentiated body with a silica-rich mantle, and then a lot of the heavier elements like iron and nickel and other pseudophiles fall towards the core. So it's expected that the core is a primarily iron-nickel alloy. However, we know that it's underdense with respect to that. So we know there must be some kind of light element in the Earth's core. And there's been several proposed, such as hydrogen, oxygen, silicon, and sulfur, but it's impossible to directly measure the evidence of these. So the question is, can we use white dwarfs to determine what the light element is? So if a differentiated planetesimal has its mantle stripped, either through a violent collision or a mantle sublimation in post-main sequence evolution, then we can get a core-rich planetesimal. And here on the left is the mass fraction of the bulk of Earth. And then here are two planetesimals accreting onto a white dwarf. So WD0059 plus 257 is one of the most core-rich planetesimals we've observed accreting onto white dwarf, with a core mass fraction of 69%, double that of the Earth at 32.5%, and much more similar to Mercury at 70%. And WDJ2100 plus 2122 is a white dwarf that I'm working on now, which also has a very large mass fraction of iron, both about 60%. And both of these have sulfur detections. So if I plot the number evidence plot, so as you go more towards the right, that's more iron-rich and therefore more core-rich. And then as you go up, it becomes more sulfur-rich. And if I populate this with some solar system objects, the Earth, the mantle, and the sun, as well as some primitive and processed meteorites. And then also, so these green points are core-rich planetesimals from the literature, which have sulfur abundances or upper limits. And then the two blue points here are the white dwarfs I showed in the previous slide. And you can see out of the four white dwarfs with sulfur measurements, three of these have sulfur abundances greater than that of the bulk of Earth, with two having super solar sulfur abundances, which could imply that sulfur is the light element in these exoplanetary cores. So next, I'll talk about volatile-rich icy bodies. So I'll talk about an oxygen excess. So we can't directly detect water in a white dwarf atmosphere. However, we can detect oxygen, as well as a lot of metals that oxygen forms oxides with. So if we take this oxygen and then we allocate it to all of the oxides, a few examples that shown there, then if we have any oxygen left over, then this could be in the form of water ice, or with other volatiles such as carbon monoxide or carbon dioxide. So this is an example of a white dwarf of Pivus 2. So WD 1647 plus 375 As can be seen here, the oxygen excess is 84%. So that means that 84% of the oxygen that we detect in this white dwarf is likely in the form of some ices. And then, yeah, so that can be seen here, where over half of the mass of the oxygen in the entire body is in water ice. So a few more interesting elements is carbon, nitrogen, and sulfur here. So if we then compare these abundances as that of the bulk Earth, so the D647 of these red squares, and then the black points is the bulk Earth, you can see very large enhancements in volatiles, carbon, nitrogen, and sulfur, as well as oxygen. And nitrogen in particular is very rare in white dwarfs. So we think that we're observing a body which formed very distant from its zero star in order for it to have retained the volatiles during post-main sequence evolution. One more interesting thing to know here is carbon, nitrogen, oxygen, and sulfur. These can only really be detected in far ultraviolet. So if we weren't able to observe this white dwarf in the far ultraviolet, then it would basically look identical to the bulk Earth. So yeah, so I hope I've come into that ultraviolet observations of white dwarfs are crucial in determining planetary compositions, and these are needed in order to determine the light element in the Earth core, as well as to explore primitive volatile-rich bodies. So yeah, these are two of the papers I spoke about today, and also I finished my PhD this January on the job market. So if anyone's looking for postdocs, I'm happy to talk. Thank you very much.
Awesome, thank you so much. Question for Jamie. Yeah, let's start there.
Given this talk and the previous one, can we safely say that the statistics of white dwarfs that show evidence for engulfment of planetesimal material is consistent with the occurrence rate of planetary systems?
Yes, so having a look at the white dwarfs that are actively accreting, some evidence of recent or ongoing accretion. So that's like abound on the planetary systems that we believe survive around white dwarfs. However, because the smallest mass stars won't have had time to become white dwarfs, yes, this is like biased towards the more massive stars which have had time to become white dwarfs.
Somehow reconcile this is statistics from one aspect and this is from another domain.
Yeah, I agree.
So they are consistent.
Yeah.
Okay, there at the top right.
Inge Kamp, University of Groningen. Depending on the abundances of the precursor star that led to this white dwarf, the mineralogy of planetary bodies forming in there could be very different. And so when you do this kind of comparison then to whatever the light elements may be in the core of Earth as a proxy, or how to account for the oxygen, how much are you biased towards the assumption of a real solar type composition, or do you allow for a diversity in original composition of these stars?
Yeah, so there's a couple of ways to correct for this. One is to observe the stars, to observe white dwarfs in the thick disk or halo, which we know are metal poor. So we have some constraint on the initial metallicity. And another is to observe white dwarfs with main sequence white binary companion, where the two initial metallicities are the same. And studies of those so far have implied that the abundances do match quite well. But yeah, it is definitely a limitation of white dwarfs in that you don't know what the initial metalist is. But if we observe enough white dwarfs, then we can get some kind of statistical constraint on that.
Okay, last time we have one question online, but also please try to keep the answer a bit short. Thank you.
So, Dewey Peters, Geneva Observatory. Thanks for the interesting talk. How much do differences in the thinking time scale affect the compositional results here? And are these relatively uniform for the sample of hot white dwarfs you used?
Yeah, so we do correct for differential thinking. So we model the atmosphere and we determine the accretion rates. And then because these are quite hot, they don't kind of have all the uncertainties associated with convection because they're creative atmospheres. So yeah, so we do correct for that.
Okay, awesome. Let's thank our speaker now and our session again. Thank you all. Next, before we go on to the flash talks, we have a short announcement on Rocky World's discussions.
I'm Limbo Christmas and Rob and Claire and all of us are a small fraction of a wonderful team behind the school. I speak loudly anyway, it's okay. Hello, oh, hello. I think you all heard me the first time. The Rocky Worlds Discussions is a monthly online seminar, which really carries the spirit of the Rocky Worlds Conference, where we showcase topics on the Rocky Worlds topics, and we have excellent researchers from all of the different areas that we've already seen people present from here. So if you wish to join the seminar series, you will can use this QR code to join our mailing list. And through that, you will be sent the Zoom link, so they happen online, but they also get streamed onto our YouTube channel, and you can also go on our YouTube channel and view past talks. So small advertisement is that the next talk coming up is on Thursday, the 5th of February. We do the first Thursday of every month, generally speaking. And the next talk will be on space weather effects on atmospheric escape of Venus. Ooh. And we also have some excellent speakers coming up. And on this link, you'll get to our website. You can see other speakers that are coming up. And it's really, really fun. It's really, really fun. So I hope to see you all online there after this week. Do you want to add anything?
Yeah, we'll add the link to join the Discord or the discussions on the Discord.
Thanks, everyone.
Okay, so before the coffee break, we'll do the flash talk session. So yes, if you see your name on this slide, please come here, form a line in an orderly manner. You will have 1 minute per person, so please try to stay on time. Oh yeah, and don't forget to vote for your favorite poster.
So, hi everyone, I'm Emmeline Decoq. I'm a PhD here at Captain. And my poster is about the work I did last year for my master degree. So we worked on linking stellar composition to the nature and mass fraction of volatile compounds in exo-ocean world. So star abundances of refractory element and metallicity are often used as proxy for planetary bulk composition. But the reliability of this approach remained debated, and so especially for volatile. And so for this study, we used stellar abundances of iron, magnesium, silicon, carbon, and oxygen, and a ternary framework, that you can see here, for example, to predict the partitioning of planetary building blocks into silicate sulfide rocks, refractory organics, and water ice for a small exoplanet and form beyond the snow line and around J, K, and M stars. And so we, okay, so if you want to learn more about all this, you can come see me near the entrance. Thank you.
Hello, everybody. My name is Ioannis. I'm also a student here at the Kaptein Astronomical Institute. Hope you're enjoying Groningen so far. My project is on photochemistry and exploring its effects using the Proteus framework. So this is the framework that we use here in our Forming Worlds group, and it's coupled with Vulkan and FastChem. And here you can see sort of like result of a simulation grid over the redox state and the installation flux. You can see also for the Sun and the M-dwarf. And notice how the parameter space that seems to be most affected is the one with lower installation flux and more oxidized. So if you want to learn more about this and talk about Proteus, Vulkan, anything, my poster is number 8 at the very end on the right. Thank you so much.
Can stable liquid water oceans form on sub-Neptunes? Now, I wish I had an answer for you, but fear not, we might have one soon, since this is my research project that I'm working on right now. The objective is to solve the equation of state of magnesium silicate for melt and solid separately, then add water, run Proteus, and see what we find. So far, I have managed to solve this equation of state for melts, validate against the existing lookup tables, and extend these up to 5 terapascals, which is great. And now the time is to add water and see what we get afterwards. If you want to know more, if you have any questions, suggestions, feedback, anything, feel free to go to my poster. It's number 9 in Ioannis's. I would love to talk to you. Thank you.
Hello, everyone. I'm Daniel Estudillo from ETH Zurich, and I have a very quick challenge for you today. I want you to look at these 3 planets and guess which one is the moon. So, not that easy, right? So if you have if you struggle to guess this or guess anything other than the one in the middle, then you have fallen victim to one of the moon's oldest mysteries. It's lunar crustal dichotomy. So if you go to my poster or come talk with me, I will introduce you to a concept that I'm trying to introduce called tide-driven magma ocean convection, which we're modeling and using to explain why the moon is basically 2 different planets disguised as one. Right. Thank you.
So hello, everyone. I'm Nicolas Monchetti from ETH Zurich. Essentially, what I do is I couple global scale matter convection models with a pressure and temperature space assessment of structurally bound water storage capacities for both hydrous and nominally anhydrous minerals. And so if we integrate that into the models together with water-dependent rheologies and melting curves, then these models can give us insight into how the water field essentially develops and distributes itself over geological timescales, which is very interesting. And specifically in my poster, I look at how different tectonic regimes essentially modify this evolution, which is very interesting because people often think that tectonic activity simply modulates the fluxes at the surface, but we found that it also has an important say in how water tends to partition the different sectors of the mantle. So if my poster is number 89, so feel free to pass by or stop me anytime. Thank you.
Hello, I'm Riona Yamada from Nagoya University, Japan. We are focusing on planetesimal fragmentation problem. In collisional growth scenario, there is a critical stage where planetesimals easily disrupted by collisions. But this view assumes that planetesimals are rocky bodies. In our studies, we model planetesimals as porous dust aggregates and conduct simulation, collision simulation. And we find that porous planetesimals can merge at even at high velocity. So this result supports that collisional growth scenario of planet formation. Sorry, I think you can find my poster at board number 87. Feel free to stop by. Thank you.
So hi everyone, I'm Nicolas Crouzet. I'm a postdoc at the University of Groningen, and my poster is about big rocks and tiny worlds hunting for asteroids with GWST MIRI. So asteroids are remnants of planetary system formation, and there are also possible reservoirs for organic compounds to be delivered to planets. Collision with asteroids also pose a threat for life on Earth and potentially on other planets. So our project here is to detect and study solar system asteroids by measuring their thermal emission in the mid-infrared with MIRI. So for now, we focus on one specific program, the MINES program, that has MIRI imaging data at 12.8 microns, and we found 18 asteroids so far. Here I'm showing on the left their flux as a function of asteroid ID. Five of them are known, 13 are new, and the new asteroids are 1 to 2 orders of magnitude fainter than the known ones. So that means they are really smaller than what is currently known. On the right, I'm showing also the light curve, so we can constrain their rotation period and shape. So this study will help understand the small asteroid population in the solar system. And please come talk to me at poster number 22 if you want to know more. Thank you.
Hey everybody, I'm Chris Worth from the University of Chicago. I'm very excited. You can see lots of exclamation points about my paper that just went on archive yesterday morning. So get it while it's hot. So basically, when we want to make a inference from our data or think about what different potential atmospheres could look like on tidally locked terrestrial planets, we have to have a model that tells us if there were an atmosphere, this is what the conditions on the planet would look like. But most of the models that we've used were developed for like the cooler, slower rotating Earth, Mars, habitable zone planets. And so it turns out that they're not valid for the hotter planets that we're currently observing with JWST. But don't worry, because I made a new model, an order of magnitude analytic model that does not use these assumptions, and we find that these assumptions could affect our conclusions at the order of magnitude level. So come to the left around the side and talk to me about that.
Hello everyone, my name is William, my surname is Brilliant, and I'm here to talk to you about the high accuracy radial velocity planet searcher 3. And look, it's opening up. And if you'd like to find out what's inside of it, I'm afraid you're gonna have to wait until you come to my poster. Number 56, just outside the coffee line. And I'm happy to talk to you about how it works, some of its specifications, how it's going to be used to find Earth mass planets around sun-like stars, courtesy of the terror hunting experiment. So come see me.
Hi everyone, I'm Mariana Sastre. I'm a third-year PhD here at Captain, and I'm going to explain you my research with emojis. So basically, I have this big question of what is the influence of redox state on the thermodynamics and how this affects the volatile release history of a planet. So for this, I'm using Proteus, the framework, numerical framework we are using here at the Forming Worlds lab that couples the interior and the atmosphere for solving the magma ocean evolution. So I found that indeed it has an impact on the timing, the melt fraction distribution throughout the mantle, and the mass and composition of the atmosphere. If you want to know how this relates to Barbie and drones, come to my poster. It's at the entrance with a beautiful Icelandic eruption. Thank you.
Hi, I'm Fabian, and this is an illustration of an ultra-hot super-Earth, specifically a magma ocean planet. It contains everything that we would expect on such worlds, like atmosphere-interior interactions and a self-consistent atmosphere composed of probably toxic gases, as well as interior dissolution and this scary quantity called oxygen fugacity. If you want to know more how these things interact, come to my poster with exactly this illustration. Sometimes I'm also there.
Hi, my name is Vasudha Trehan and I'm from University at Albany State University of New York. Thank you for having me here. So my research is about developing a Bayesian machine learning algorithm to predict atmospheric absorption spectra. So the model will be trained on both actual data from our solar system and synthetic data from Rocket 3D GCM model. So the idea is a resulting study will act as a forward model so that the planetary parameters can be inferred given the atmospheric absorption spectra. And over here, on the top is basically a synthetic spectra from Rocket 3D. And what we are trying to do is we are trying to bend the spectra to form histogram approximation to the spectra. And then we are trying to predict the height of those bins. And height of those bins is basically the function of planetary parameters. And here we are looking at 30 planetary parameters. So it's a 30-dimensional problem. Over there on the hypothetical sheets, it shows 2-dimension. But if you want to know like how I'm tackling the 30-dimension problem and you want to know the concepts I use, please stop by my poster. Thank you.
All right, thanks everyone. Let's enjoy the coffee break and we will be back at 11:05.
Thank you. Okay, so we are going to start with this session before lunch. Our first speaker is Heike Rauer. She's from DLR, and we'll talk about exoplanet search. Do you have the talk? Okay, how about current and future instrumentation? I'll let you know when you have 5 minutes. I'll let you know when you have 5 minutes.
Okay, great. So welcome everybody. In fact, I will talk more about future instrumentation and less about current instrumentation because I already have too much slides. Doesn't work? Wrong direction? Wrong direction. All right. I just listed all these questions we are all interested in, and I heard so many exciting dreams and models, theories already at this meeting. However, if we want to detect extrasolar planets, we are down to a few techniques that that allow us to access these targets. So I guess you're familiar with them. This is just a few of them. Radial velocity done from the ground, the technique that discovered our first extrasolar planets, transits, the method that allows us to do a lot of things, as I will show. However, with the restriction that we can only observe systems that we see edge on. Astrometry, an upcoming technique. Again, an indirect technique. We measure the position of the central star on the sky to infer the orbiting planets. The only technique here that allows us to see the target of interest directly is direct imaging. And we are fortunate that we already have some data. We can see one system. And I mean, in the public outreach talks, I always make sure that people understand that they are the first generation of mankind to actually see a planet orbiting another star with our own eyes. And I think it's really something that, even when I say it 100 times, I find it exciting personally. Yeah, it is great. And it's a great research field to be in. Then microlensing and timing, which is a variation of transits as well as phase curves and so on. The techniques, if you look at the evolution of the techniques over time, first you notice the enormous increase of planets that we know, but you also see the techniques are don't all deliver the same amount of planets. The most successful technique these days is the transiting method. This is thanks to the space telescopes that were up and are up and running, Kepler and TESS mainly, followed by radial velocity. And now microlensing coming in, but all the other techniques so far have made little contribution to the detection, although this will change in the future. If you look in terms of numbers of planets that we know, there are thousands of candidates, several thousands of planets. But you as modelers, when you look for comparison targets to your observation, or to your models, to your simulations, you notice that when you want to compare two planets with known parameters, the numbers are still actually quite small, and we are talking about hundreds and not thousands, if at all. Now, I don't know if you can read the table. I don't know if you agree with me with this table, but I made a table to show from the different techniques, the main techniques, what can we actually learn? And I divide into fundamental parameters. That's like we know the orbit, we know the mass, we want to know the radius and some population statistics. And then we want to learn more. That's physical characterisation, the mean density, the atmospheric composition, phase curves, Love numbers, spin orbital obliqueness. And you notice there are sticking out, that's the transit method, where you have across in almost every column except the spin orbit angle. Here we need the radial velocity method, definitely. For densities, we need to combine transits with radial velocity or with astrometry. So clearly, different methods deliver different kinds of information about our targets, and that already tells us we need to have as many instruments, as many different instruments in the sky as possible. The other thing is if you look in the literature, most of these characterization information are done for gas giants, mini Neptunes or mini gas planets, close-in planets, but they are not done for Earth-sized, temperate Earth-sized planets, because simply we are not able to do so in terms of signal-to-noise and accessibility yet. Also, in terms of detection method, these detection methods have different parameter discovery spaces. We have the transit method, which has a bias to short period planets, and we want to extend the transit method to Earth-like planets in the future, and I will talk more about this, of course, later. We have radial velocity that can go out to Jupiter-like planets, real Jupiter-like planets. Direct imaging in this moment is far up here, young, hot, gaseous, big planets. And then microlensing coming in here. If we talk about rocky planets, so for this conference, I mean, don't nail me down on the exact position where I put the rocky planet separation. It's just for illustration. But we are somewhere down here, yeah? And you will tell me as modelers where exactly this line should be. But we are down here, and then we talk about radial velocity for close-in. We talk about transits and microlensing. So these are the methods we are facing, and I want to go through the missions now by method, starting with microlensing to give you an overview. However, before doing that, just to recap again our lack of knowledge today. Some of you might have seen this. This is a plot I made. I started already a long while ago, but it's showing the density, the mean density of planets versus mass. And you see this typical V shape, the gas giant planets, the Venus and Earth are up here, so the squares are solar system planets, and then Uranus, Neptune here. So here we have the transition between sub-Neptunes, and super Earth and Earth-sized planets. And the point is, if I limit myself to only 8 days orbital period, this plot is still pretty empty. I admit I made it N24, but it doesn't change. And it doesn't change because we need future instruments to make a change and to put more dots, yeah, at least the mean density. For me, the most fundamental parameter. Still, I know there's a lot of degeneracy when you want to infer core mantle ratios and composition and tectonics and all of that. But if you have no clue on the mean density at all and no constraints, then you're pretty lost. So at least this, you see how limited we are today still in our knowledge. So let's see what's coming in the air. Why is that? Why is that? Here, this is a plot showing Kepler data, and you might have seen this. This is the knowledge of the radius from Kepler observations. The masses determined from radial velocity in brown, and the orange and green are the overlap. And you see overlap between radius measurements and mass measurements are mainly found in the region between 10 and 16 magnitude. 10 and 16 magnitude is pretty faint, and that's not really feasible for large-scale surveys. You need bright objects, and if you want to observe atmospheres on these targets, you really have to go bright. So that's a problem. That's why we have so many thousands of planets known, but so little characterized. The planets done by the past surveys were too faint. Yeah. So where are we now? This is a plot we made with some US colleagues in 2021, so some years ago, and I updated it a bit to see where we are today. So today, at the time of the plot, was 2021. Now, today, we are here, about at the green line. And we see the US-led, ESA-led space missions. We now have TESS. TESS already addressed the point that the targets of Kepler were too faint. So TESS is looking at bright stars, detecting them and measuring the radii with the transit method. TESS is still running today. James Webb is up, meanwhile, delivering exciting data on atmospheres, really great stuff, and more to come. We have Cheops on the European side still running. Gaia is up. Euclid is ready to launch. And you see here the list of topics. That's how we saw the development of the field 4 years ago. Going from hot Jupiter's basic characterization to the area now, where we are now, on exoplanet population and atmospheric diversity. Going to the next phase, which is habitable Earth-like planet, exo-Earth, M-dwarf rocky planets, biosignatures, and even frequency of habitability and biosignatures. And we know now at the time of writing, there were a number of concepts up, which is now emerging to the Habitable Worlds Observatory in the US and the LIFE concept on the European side. We also have a new mission addressing the topic of populations, and that's the Earth 2.0 mission from China. So let's have a look on what's coming and where we are with these missions. And I go through it by technique. I start with the microlensing missions. There's one microlensing mission already up in the sky. That's the European-led Euclid mission. It's a 1.2 meter telescope. The main goal of both missions is not extrasolar planets. They are there to investigate dark energy, dark matter, and things like this. In particular, for Euclid, that's true. So when I searched again for what does Euclid do for exoplanets, and what they say, they will support the Roman telescope mainly, and they will go for exoplanets as a legacy part, but they are not doing this right now. So the Roman telescope is up for launch in October this year, very exciting. The telescope size, 2.4 meter, pretty big, pretty small field of view, because as I said, they are not a survey for exoplanets, but they have two goals. They have microlensing, which is their plus transiting planets. So we will see this mission twice in my talk. And it's designed to give us an estimate of the occurrence rates of planets. And if you look, there's one comment about microlensing missions. Microlensing events are pretty rare. It's even worse than transits, I know, maybe at least not less. So what are they doing? They look at a place in the sky where you have many, many target stars to observe. And the way to do that is to look towards the galactic center. So that means by definition, we are looking at very faint target stars, very difficult to characterize the objects further. So that's already clear from this plot. However, you also see again the complementary of the methods. We have transits and radial velocity here in our neighborhood. And then the microlensing planets, we are probing different areas in our galaxy. So again, I advocate for having complementary methods going on. Now, what's expected from a Roman? Here we see again this plot of showing the planet mass versus distance with all the detected planets, plus the ones modeled for for W first, now Roman, called Roman. You see very interesting target range for microlensing. It's exactly at the right spot where we want to get our rocky temperate planets. It goes down to Earth-sized planets, even smaller, and it's the target range is 1 AU and beyond. Yeah. So the expectation from the Roman team is about 1,400, so more than 1,000 cool exoplanets. The problem with microlensing is the determination of the planet parameters, because typically we don't see the lensing star that has the planets, but they expect about half of the sample would give some mass constraints of our planets, at least when we have bright lensing stars, so we can see the stars afterwards and can investigate it further. So microlensing technique is really something to watch out for. Less for detailed characterization of planets, I would say, but an enormous contribution for statistical analysis of cool extrasolar planets, of eta Earth, yeah, in exactly the range that we want, and that's 1 AU and beyond. And then, of course, there is the other thing about microlensing. They can also detect free-floating planets. That's something no other technique can do. Then transits. I already pointed out the capabilities of the transit missions and the natural interest in this technique. It started all with Corot, and I made here some Corot, then Kepler, K2, TESS, and Cheops. And for me, there are milestones. Corot was the first mission that detected rocky exoplanets outside the solar system, which I think is a milestone. Yeah. It was not a temperate planet, 20-hour orbit, pretty hot, but it was the first one. Kepler is another milestone. Kepler, for me, is the beginning of exoplanet statistics. Still, as I said, constrained to the close-in planets, but it was the first one. TESS and NASA by NASA builds on the statistical characterization and gives us a complete figure for the close-in planets within about 80 to 100 days. And Cheops has on purpose not detection, but characterization as its goal, and that is the precise radius to help constraining it doesn't resolve your degeneracies, but it helps resolving the uncertainties in your models coming from observational error bars. Right. So that's where we are today. So what's next? And let's come back to the Roman telescope. I said the Roman telescope has two techniques in its goals, the microlensing techniques and the transit technique. And well, they go down to 20, oops, oh no. They go down to 21st magnitude, so as I said earlier, pretty faint stars. However, if you look at the expectations for transiting planets here from Roman, yeah, the yellow are the ones we've seen before, the microlensing planets, but now green and blue, the transiting planets, you see in the range of gas giants down to almost Neptune-sized planets, we will get a lot from Roman. So Roman launched in October. You keep your fingers crossed for the launch that everything goes well. With microlensing and with the transiting planets of gas giants, it will bring us a huge step forward in terms of statistics of exoplanet populations. And especially interest, of course, is in this parameter range where we have both microlensing and transiting in the same parameter range. All right, now obviously my finger wants to come to this mission. I don't know why. The next mission to launch with the transit method is Plato. We will launch in the first quarter of next year, probably in January. It's an ESA mission. I will spend a bit more time on Plato. I hope you will forgive me. Plato has 26 telescopes, small aperture, covering a very large field of the sky to get enough targets. Our main target range goes, the magnitude of our stars goes down to magnitude 11. And that again is like TESS addressing the fact that we want to get characterization and allow for future characterization of atmospheres and so on. So the baseline of the mission is to have 2 targets fields with 2 years each. And the goal, as I said, is to detect and characterize planets for radius, mass, and age. We are ready. The satellite is ready. The satellite is just undergoing its last tests. So it's just to show you that it's real, like Roman. Yeah, both satellites are there waiting for launch. The methods. The point about Plato is a big lessons learned from Kourou. That is another reason to go for bright stars. And that is we can then combine the transit method with astroseismology from the ground. Not only ground-based radial velocity observations are much easier for brighter stars to get the planet mass, but we also get the stellar parameters much more precise. Because the transit doesn't measure, it's the only method that measures the radius of the planet directly. That's a statement I often read. Well, it's true if you know the parameters of your star. So you need to know your star. And the other thing is, by astroseismology, will give us the age of the star. And the requirement is to get the age of a solar-like star to 10%. So the mean density and age. Just quickly, why are we doing Plato? To repeat this again, this is a plot showing the stellar mass. So here's the sun. Versus this orbital distance of planets, and the green band is the habitable zone, moving closer to the star as you go to M-dwarf stars. All these circles are planets, and those that are what we call well characterized with less than 10% mass, 5% radius precision, something where you can start to get a hint on core mantle separations. Yeah. Are very few, and obviously nothing in the, except the solar system, nothing in the habitable zones of solar-like stars. So that's what we want to address with Plato. We will observe a field in the south. And here it is. Here's the Plato field with this, the colors indicate how many telescopes are observing the same spot in the sky. You see how big it is. The yellow line is the continuous viewing zone of TESS. It's also the point in the sky where James Webb can always point at a target. So we can see we can see the overlap and the input to James Webb from this already. Here, the northern field has on its edge the Kepler field. Is including the Kepler field. However, we go south. We start with the southern field. Why? Because only in the south we have the instruments that can give us the planetary masses to the required 10% precision. That's why we start south, and we will stay south as long as possible. Just for those of you who might want to observe known planets further, we have non-transiting planets in the field. We have a lot of test candidates in the field. We also have non-transiting planets in the field. Non-transiting means phase curves. And of course, as a byproduct, not only detection, Plato will also deliver white light phase curves for those interested in this. This is a comparison of Plato and TESS. All the black dots are TESS candidates, TESS targets. Here's again the TESS continuous viewing zone, the yellow circle. The red circle is where we will get at least 4 TESS sectors observed. So there's a lot of overlap, and you might say, well, why do you need Plato then? Well, Yoshi, who is here somewhere? There. So any question to this plot goes to Yoshi. But I like it because it nicely compares the detection capabilities from TESS for 12 sectors with 2 years of Plato observation. And from this, you can clearly see an Earth would be here. there's no chance with TESS, even including the continuous viewing zone, to detect an Earth around the sun. With Plato, we are here in the green. So now you can argue with me, Heike, is it enough or not? Well, you don't argue with me. We want to observe longer than 2 years. Yeah, it was just due to constraints, discussions with ESA. Of course, we want to observe longer. We have time for 4 years. We have fuel for 8 years. So, but it shows the relative comparison very nicely. And this is a very complicated plot. I don't know if you distribute the slides, then you can look at it more carefully. Yeah, so I'll leave it in. The message here is this. These are histograms comparing TESS with the green is Plato for what type of planets they are. And the yellow line marks all planets up to 4 Earth radii. So that's what we expect for G-type stars from TESS, and that's what we expect from Plato. So it's not only that we cover the larger orbital distances, it's also that we will give you much more small rocky planets to model than we get without Plato. So you really needed to get constraints on your observations. And I'm often asked, what's the expected yield? Let's just go to the important line. That's the bottom one, bright stars, planets with 2 Earth radii, up to 2 Earth radii, and 2 + 2 years, so 2 fields prediction, and the prediction is from 0 to over 120. And we are pretty honest about this. The uncertainty comes from eta Earth. And if you take publications, the extreme is 90% of the planets, 90% of the stars have an Earth-like planets, then you're over 100. If you say only 2% of the stars have an Earth-like planet, we will detect nothing. Okay, so stay tuned and let's see. The important point here is whatever happens, we must be able to nail this down with an error bar, yeah, to really give a constraint. So personally, I believe we are somewhere in between, or probably on the lower end, but somewhere in between, as usual. Now, meanwhile, we have a new mission on transits coming up. The Chinese 2.0 mission, it's scheduled for launch, also not far from now, in 2 years from now, 2028. This is an interesting concept. It's a kind of mix of the previous ones. It's also a multi-telescope or multi-camera system with 6 times 28 centimeter aperture. That's about, each one is about the aperture of the Cheops satellite, but 6 times. It also has a large field of view, and it will return for the Kepler field to the Kepler field and reobserve the Kepler field, and of course much more because the field of view is larger, much larger than Kepler. So for 4 years, so in addition to transits, it also has a telescope for microlensing, so it combines both methods, and is expecting 10,000 of planets, transiting planets to come. And this is their comparison to the Kepler mission, and you see how they, in particular for the Neptune-sized planets, but also super Earth-sized planets, what's the expectation coming from the Chinese mission. So this again is a very important step complementing our population studies for all the various classes of planets and population studies of characterized planets with well-known radii here in this case. That's also a complicated plot, but for those who want to read this afterwards and get a better understanding of transit mission, what matters? Well, in transit missions, what matters first is telescope size. It's just a photon collecting area. If you go for bright stars, your photon collecting area should be small, otherwise you overexpose. Yeah. So we have the small telescopes that go for characterization from Corot, TESS, Cheops to Plato. And then we have larger telescopes, Kepler, larger and Kepler and Roman, that go for fainter stars, but in this way also produce high numbers of planet populations. And then the other thing that matters, of course, is the sky area covered. You can have a smaller aperture, but if you step like TESS, you cover the whole sky, and then you have a huge search area. So at the end, if you look at these and you say, I want to have bright targets for my atmosphere follow-up, you're here in this range, and you see Kepler was just touching it. Earth 2.0 is then Plato and TESS are the ones that really target for the bright magnitudes to provide the future atmosphere follow-up studies. What's coming next? Well, that's done by James Webb. There are people here in the room who know this very well, and already we get a lot of atmosphere spectra from it. It's 6.5 meters, just to recall that. With James Webb, we really get the detailed investigation of our planets. It's the largest telescope, the best quality we have today, and we can observe dedicated targets with it. The other telescope, the next one to launch, is Ariel. Ariel's goals are exoplanet atmospheres with a 1.1 meter class telescope working from the optical range to 7.8 micron. And Ariel's goal is a survey of extrasolar planet atmospheres. So here we go from detection population studies to atmosphere populations, atmosphere statistics. And so this plot for James Webb, first I go to is illustrating for the two instruments on James Webb the target ranges for transits, eclipses, and phase curves. So this is again radius versus planet radius versus semi-major axis. And we can see here in both cases where it's overplotted on the black dots. That's the population of known planets. You can see where we are with James Webb targets now. We are for the close at Earth radii. We are here in the close-in planets and planets around M-dwarfs also. This is we know that, and we are touching here on for super Earths. We are going outwards to about 0.2, 0.3 astronomical units. We are not touching the 1 AU range here, of course, because we don't have the targets. Ariel versus James Webb. It's interesting, of course, because in terms of instruments, both missions are rather complementary. If you look at this white paper, recent white paper, a very interesting one about Ariel and James Webb synergies, I think it's very nicely demonstrating here again how both missions should work together and how both missions will complement the statistical overview with the dedicated studies and the detailed investigation by James Webb. Oh God, so I have to move on. This is also showing the Ariel, James, and Plato, Ariel, James Webb, Plato overview. So again, of course, here there will be new planets detected from Plato. I hope I convinced you on this, that then can be surveyed with Ariel and Plato if the teams decide to do so. So what's the big dream? Yeah, this is a plot I made more than 10 years ago to convince ESA to having another exoplanet mission. And this dream included the evolution of planets, included the evolution of rocky planets from magma oceans to plate tectonics to the development of life and biosignatures. And it includes for me the question, are terrestrial planets always ending up like an Earth? You know, maybe they are rocky and they are habitable or not habitable, and they are a bit different than the Earth. And answering this question, which is my big dream, yeah, I would like to understand this. And I think you share this dream. But answering this does not only need Plato, it does not only need James Webb, it does not only need life. We have to have all of these missions together because it's so complex. It is so complex. So we have to see what we can do, combining all the different techniques, and in particular also go to biosignatures. Yeah, this is a plot from the Habitable World Observatory papers or web pages. You see the evolution of the gases in Earth's atmosphere. You believe it or not, when ESA asked me, which requirement do you need, which requirement do you put on the age constraint for Plato. How precise do you need to know the age of a terrestrial planet? I thought, what the hell, how do I know? I only have this system and I only know, it developed like this. I have no idea what is typical and what to put. What I did, now I can say it because we do it. What I did, I took this plot. Yeah, I took this plot of the evolution. And I saw that the atmosphere of our planet developed in jumps. And if we ever get a good statistic of temperate rocky planets with atmospheric composition, yeah, that's far. It's far, far in the future. But if we ever, and we can put this on an age comparison, we will see whether there are planets where everything else is the same, so we really need a lot of statistics, where everything else is the same, but how they develop with age. In the same way as the stars. I'm inspired by how did astronomers understand the evolution of stars? We don't see the evolution of stars. We are too short-lived. But we see stars with different ages in the sky, and we were able to link that together and to understand which stars are different types of stars, and which stars that we see are the same stars with a different state of evolution. And that's my big dream. And for this, we have to combine everything, and I have to speed up, which I will do. There are 2 missions coming up, as you know very well, the Habitable Worlds Observatory. The main aim to characterize 25 Earth-sized exoplanets in the habitable zone. So you will say, Heike, that's not enough for the statistic I'm talking about. And yesterday, Tom dragged me into a Splinters breakout session where he put up the question, if you have 200 billion euros, what would you do? Yeah, with 200 billion euros, we can get it. Okay, so we have the Habitable World Observatory coming up with different instruments covering from the optical up to the infrared, near-infrared, including UV multi-object spectrograph. I have to rush. And on the European side, we have LIVE, an interferometer concept, unfortunately not yet officially studied by ESA, but we should push them to do so, to follow up, because both instruments complement itself very nicely. And again, there are papers now showing the complementary of both missions, HWO targeting at the optical and near-infrared range, and then LIVE, including the ozone and the CO2, the strong, very strong 15 micrometer CO2 band. I skipped that because I want to go to the fine, just leave this up for text. So again, I think we have to push if we want to have these big missions. We need to continue pushing. Time is hard. Money in the society is needed elsewhere. We have to promote the understanding that still science like this is a question that should not be dropped completely, but has it's a mankind question. So whatever happens, these questions, whether we are alone in the universe or not, will always remain. And to do that, and now to go the big next step needs a lot of money. With 200 billion euros, I would build a super life. Maybe you have other ideas. The important thing now is to keep the interest of the agencies and the politicians in our science, in our questions. And when I see all of you young people, and then at least in the community, it's very strong. We just have to transport that. So thank you.
Okay, questions for Heike? The one. Can you wait for the microphone so the people online can hear as well?
Thank you. Jean-Philippe Beaulieu, Institut d'Astrophysique de Paris. So I take my Roman hat because I'm one of them. So there will be my cleansing talk by Natalia, but I will comment about the transits. So indeed, you will have close to 100,000 transits to be detected, but the magnitude is 15 to 22, 23 in H, and it is in a very extinct field. So it means in the V's, you will have, it will be more between 19 and 25. So no follow-up, nothing but a lot of lots of light curves. And one thing that is interesting is that the data will be public immediately. So it means everybody, even non-US, have access to the data, and there will be also some computing resources. So if you have a team of young people with team ups, decide to go after Roman the transit light curves, you can basically get resources, computing powers, and access to the data, and have complete freedom to do it.
Okay, thank you very much for this information about Roman, and we all keep fingers crossed for launch. And we are happy it goes ahead.
Any other question for Heike? Yes?
Yeah, Will Meisner from Carnegie Science. Really great overview of what's coming up. I had a question about Plato. So I was wondering when you showed those really interesting plots about comparing like the test yields and the Plato yields, is the fact that the Plato yield goes so much further down because it overlaps with the test field, or is it sort of independent?
No.
And does overlapping
No,
with
it's
the
despite that. It's despite the fact that the test continuous viewing zone is in the Plato field. We still get new and much more small planets.
But does that overlap like help push it down to lower radii or more distant orbital periods, or is it kind of independent?
No, it's independent.
Okay.
That very slightly adds to it, but just slightly. We look for ours, but it's just okay.
I see another question there.
Thank you. William Brilliant, University of Cambridge. Assuming these space missions go ahead, what would you say should be the priority over the next few years, especially in terms of making sure we have the facilities to follow up and make use of the information that is coming? What should we be preparing for, or how should we do so?
I'm not sure I understood the question. What we should be preparing for what?
Sorry, so assuming these space missions go ahead, in your opinion, what should we be doing to prepare for the data that they produce?
You should begin to prepare. So observationally, I think we should help our radial velocity people to improve their instruments to get the masses. I mean, from an observer point of view, all we can do is to increase the error bars. Okay, it doesn't to resolve degeneracies in the solution. The understanding of the problem is what you're already doing. In this sense, the theory part of our field is ahead of the observations. You're much more detailed to what we can actually detect and observe right now. So if you do your models and also add predictions what we should observe to give guidance to how much exposure time, what to look, what to ask for, define, help HWO Live to refine the requirements. That would be good. If you ask me, what shall I do now?
Yeah.
Just to put, Shai Zucker, Tel Aviv University, just to put things in context, you mentioned that free-floating planets have not been detected yet. So
no, have been detected.
Yeah, there have been detected candidates, but 3 weeks ago it was published, the first one that was the distance, the degeneracy of the distance was broken, and it's confirmed using Gaia and KMT, so there is from microlensing.
Yeah, but I didn't say they can't do it. I said they can do it.
No, what I remember you said is that so far they have not been detected or confirmed. So there is one that was confirmed only recently.
No, I pointed out. I just wanted to point out that microlensing is the only technique that can actually do it. Yeah. And,
okay, so we agree.
So.
Okay, maybe one final question. There is a lot of young people in the audience. Then maybe you can say a few words of how they can get involved in Plato or when the data is going to be released in case they don't know.
Oh, yeah. That's a good point. So Plato data will not become public immediately, not all the data. So we are now one field. So we observe more than 200,000 targets in our statistical sample. One field is a bit more than half of that, so 100,000 targets. They will become public as soon as they are produced. Yeah, so data come down, light curves will be produced, and when they are validated, it's about a year, up to a year, hopefully earlier. Yeah, but there's some margin at the beginning to whatever, yeah, for debugging if necessary. But this statistical sample will become public immediately after the light curves are produced. And these are stars. Yeah, most of them, we have something called the prime sample. There's a matrix how this is produced. There will be publication also more, but mostly say 11 and fainter. So they are public 100,000 light curves to play with as soon as they are available. Then the brighter target, that will become public later, 1 year later, together with the planet parameters. And why is that? Well, first, we are different than the US. In the US, NASA pays for everything. And NASA pays for everything, and NASA is a state-funded institution, and then they make the data available, and they don't fund the data processing, and it's public. In Europe, it's different. In Europe, every country and every institute pays money to build the mission. And honestly, the people who give us the money to do it, they want something in return. And what they want in return is, in Plato's case, up to 20,000 light curves that are analyzed by the consortium. That's one answer to the question. The other answer to the question is that I think one of the big problems we have in the field now is to understand the biases. Yeah? Why is there not more coming out of the Kepler populations? Why are these eta something still so uncertain? And why is it so difficult even in radial velocity? It's so difficult to understand the biases of the various ways how the data are analyzed. So the result of Plato should not be just light curves. The result of the core sample of Plato should be a catalog where you know how has it been analyzed with state-of-the-art methods. It's traceable. It can be updated if you have a better method. Fine, yeah. But it's a catalog that we can then really use for statistical purposes because it has been produced in a homogeneous way. It does not exclude that, of course, as soon as the community and everybody gets a hand on the data, will do whatever they want. Yeah, but from the consortium, we want to produce a catalog that is produced in a, of course, transparent way to the community, but in a homogeneous way so you can interpret it. That's why for my science, it's my science answer. The other was a formal admin answer, but the science answer is that. And that's why I urge everybody to work together for this homogeneous catalog. Now, if you ask me how can I enter, the consortium is open. It's still open to be part of this core science analysis. There's, however, an entrance ticket. You must write us an application, and you must tell us what you do, what you contribute to the data, to us. Now, if you say, I don't know, and there are so many work packages already, and the team is already so big, and everything is done, well, I know it appears like this. It's clear because we are working on this since 10 years, and we have accumulated the community before you already. So now you're coming. So write us and tell us what your expertise, what you're interested in, and then we can also give you guidance where in the consortium your expertise would fit. Then we bring you into contact with the people who are, I'm assuming, well, maybe you have a hole, yeah, then that's great. We fill a hole. If you don't have a hole, we bring you into contact with the people who already work in that field, with the community, and then we see how you can be integrated. So it's for Europeans, yeah, for Europeans and part of the ESA member states, that's a relatively, I mean, there is still room for you to come into Plato. The only condition I make is that if you're part of the consortium, you're required to work with us as a team towards this homogeneous catalog. Yeah, because that's why we have a consortium. Otherwise, we can just give it free. And so, as I say, it's open still. But you have to also say what's your contribution. Yeah, make a contribution.
Okay, let's thank Reike again. And our next speaker is Natalia Rezzini. She will tell us about Euclid and HST to describe a terrestrial planet around one star of a binary system.
Okay. Can everybody hear me? Oh, thank you. Yes. Hello, I am Natalia Rezzini. I'm a postdoc at the Institute of Astrophysics in Paris. I am also a member of the Euclid Consortium and the Euclid Exoplanets Working Group, working with all these people. And today, the line of work that I'm going to present is basically how a part of our preparations for the upcoming microlensing survey with Nancy Gray's Roman Space Telescope. But before I start with this, a bit of maybe not everybody's very familiar with gravitational microlensing. So how we detect a planetary system with this? Basically, the planetary system has to be aligned with the background source star and an observer. And in that case, the gravitational field around the planetary system is bended because of the mass of the host star and the planet. So the light rays of the source star will follow this bending. And as a result, we're going to see a lot more light coming towards us. So this will be the magnification because of the stellar lens. And the anomaly is what we expect to be a planet. Now, oops. As already previously said, with microlensing, we detect mostly exoplanets in 1 to 7 kiloparsec distance from us. So basically, you cannot do studies about atmospheres or interior. So at this point, I've probably lost all of you, but now I got you back. And but the important, why we do care about microlensing is because it's unbiased to the host star mass and type. So we can detect different types of host stellar masses and different types of planet masses. So it's quite important for population synthesis. Also, it's very efficient towards the close to the snow line, which is where we expect planet formation to occur. And for this reason, there is a microlensing survey up hopefully coming, because we want to have more purple dots and with higher precision. So typically, from a light curve, we will have the duration of the event, and we'll have hopefully some information about the source star, which will give us information about the planetary, about the lens star. And then we can always sometimes have a microlensing parallax, which will occur if we observe, if the observers are very in far distance between them. So maybe on the ground and the other on the sky, like what the person just said for the free-floating planet, where you have Gaia, and also we have Ogle and KMT-net on the ground. And using the microlensing parallax, they managed to break the degeneracy and have to know where the distance and the mass of the free-floating planet was. Unfortunately, there are not a lot of cases yet, but they will come, thankfully, with Roman. And then we can also have the planet-star mass ratio and the planet-star separation in units of angular Einstein radius. So basically, this is a method to do, population synthesis and demographics, but you don't actually get what you need, which is the planet mass, the host star mass, the separation, and where it is located. To solve this problem, we have been using the high angular resolution follow-up observations, mostly with Keck and HST. Why follow-up? Why high resolution? Because it's always better to have 5 pixels for one star than 5 stars in 1 pixel. And also, if we wait long enough to do the observations, then we will be able to have source and lens resolved, which means that we can have a precise measurement of their separation, meaning the relative proper motion, how fast they move. And because we know the length of the event, how long it lasted, we can have a very, very precise measurement of the angular Einstein radius, which will give us information about the mass of the planetary system. We can also have, as you can see, the magnitude of the lens, which we didn't have before. So this will give us information about the host star, something that you couldn't have before. So basically, if we combine, the parallax with angular Einstein angular Einstein radius and the magnitude of the lens, we can have basically we can see where they reach the point, and it will give us precise measurements for the mass and the distance and the separation. And of course, it will also confirm if this is a planetary system or if there were degenerate seasonal light curve fitting. I have shown here some of the work. So this is something that we have been doing for over a decade. And there's a lot of interesting works that have shown that how this works. And I encourage you to go and check on them. And so using this as a study, there have been a lot of case studies showing that if Euclid observed the Raman fields before the microlensing survey, then it will help us constrain the upcoming future microlensing planets that will be discovered with the Raman. How this will happen? Because basically we will catch them before they blend. And these observations did happen. In March 2025, Euclid changed its orientation towards the galactic bulge and did spend 29 hours. Here you can see the footprint of Euclid. And in a Gaia image. And here you have all the microlensing events that have already been observed, discovered through the years. And with red, we have all the microlensing planets that have been discovered, and they are in the Euclid fields. And with the black dots, we have also HST data. So there is also a large HST galactic bulge survey happening. Even now, it's led by Sean Terry, who is at NASA Goddard, and it has the same exact purpose as Euclid, to observe the Raman fields before the Raman microlensing survey. And there are a lot of overlap, as you can see, and a lot of planets that overlap. So our work here is to start with these planets. There are 52 planets in total. And let me explain. Microlenses have never had this kind of observations before. Okay, this is a whole new Earth. We're not only creating maps, we're creating roads, bridges, as with Sean we like to say, for the tools, the existing tools, to pass through the next generation. These are stars that we have never observed before, fields that they're so crowded, it's with extinctions, it's insane. So there has been a lot of work happening, and these 52 planetary systems are really helping us construct the path in order, once Raman happens, we will be able to, go on attack. And this brings us here with me talking to you about one of these events, which is a terrestrial planet orbiting a very low mass star in 1 AU orbit. And that star is orbiting another very low mass star in about 15 AU. So this is an event that occurred, well, it started around 2012. It's a very long event, and for this reason, the authors claim that they were able to observe the microlensing parallax, which is why they have very precise mass and distance and separation. Well, is this actually true? So, no. This is the light curve. There are a lot of things happening here. But the main thing to keep is that this is the main event, the main magnification. But around almost a year before, they have observed with Ogle a bump. And this bump is basically what we expect to be the component. So this is So this is basically not the host star, it is the component of the host star. And this is the reason why they believe that this is a binary system. Now, these are the observations. We have 4 follow-up epochs with Keck in 2013. So this is the event. This is the target. As you can see, source and lens are blended. With Keck 2020, we start to see a bit of the lens. HST 2025, we can clearly see that there is a less coming. And Euclid, I cannot show because this is going to be part of the second data release for Euclid in end of June. And actually, I cannot show you any results because these are going to be also in the data release. But what I can say is that for the separation, I can see that the angular Einstein radius that they have predicted lines up. So I'm pretty confident about the masses, but the fluxes don't really line up. And okay, this is also like the full Keck image, and you can see this, and it has been a real pain to actually model this. But anyway, so let's go back to the light curve. And here you can see I have Ogle and MOA 18 and 15 years of baseline. So these are the main two microlensing surveys that observed the event. And as you can see, there is a trending in the light curve. And this trending is probably caused, so this is our target, and these are two very bright stars. Here you can see it in the Ogle frame, this is the Keck frame. And these very bright stars are going towards our target, but also they're variable. And this is the microlenser's absolute nightmare. Not only it's a triple star, yes, but it's also contaminated. But it's cool because we're gonna learn a lot of things. So my takeaway point is we need long baselines, and that is a problem for Roman, but we're handling it, and Euclid and HST are going to help. Wait for the data release, 26th of June. There will be a lot of cosmology papers, which are boring, but there will be also our papers, and thank you.
Okay, questions for Natalia? I have one though. I didn't fully understand how is that you can use one mission to kind of predict what you are going to observe with the other. Can you explain that a little bit more?
We don't predict, we just already have the frames. And then, Roman will be observing, and we will, microlensing events will be happening. And then we can go back to the Euclid frames and see, oh, how is that?
Oh, it's the other way around.
Yes,
okay,
so it's
okay.
inverse.
Okay.
We cut it before it blends.
Got it. Okay, any other question? Then let's thank Natalia again. Next speaker is Claudia Llano Muñoz, telling us about first results from SPIRIT, a CMOS detectors for exoplanet around ultra-cool dwarfs.
Hello, everybody. Can you hear me okay? All right, I'm Claudia, and I'm a PhD student at the University of Cambridge, and I work in the Speculus collaboration. And I want to share with you some of our first results with the SPIRIT CMOS infrared detector. And as a way to keep all of you's attentions today, I've hidden the little SPIRIT logos everywhere in every slide. So if you manage to find all of them and you are a PI, you get a little prize. So I don't have to convince you why we are interested in cold stars for finding habitable planets and rocky planets in general. We have heard a lot about it during the week, but in general, they allow us to make the best of the observational biases that we have in our detection and our characterization methods. But for this talk, I'll be focusing on ultra-cool dwarfs in particular. So in the HR diagram, they are these bottom right corner here. And we define it as stars that are further M7, so M7 and brown dwarfs, and usually colder than 2700 Kelvin. So for example, the TRAPPIST-1 system is in an ultra-cool dwarf. And a survey that looks into these ultra-cool dwarfs is the Speculus collaboration. Mathilde, 2 talks from now, is going to be telling you more about it in more detail about our program and our goals. And for now, I'll only focus on our Southern Hemisphere Observatory, which is the SSO in Parallel in Chile. We have 4 1-meter telescopes named after the Galilean moons, and they're equipped with Andor CCD cameras. The wavelengths that we observe on the left here is our whole coverage, and we observe in the visible and the near infrared. We obviously want to move into the infrared to observe the ultra-cool dwarfs, and we have a special exoplanet filter that it's I+Z beyond 700 nanometers to start observing the near infrared window where these ultra-cool dwarfs start emitting more strongly. So why are we not going any further? Well, as you probably know, observing the near infrared from the ground is very challenging. There are many reasons for this. First of all, the instrumentation itself is limited. because all our CCD cameras are made with silicon, and silicon has a band gap at 112 electron volts. This means this is 1 micron roughly, so anything beyond 1 micron we cannot observe using CCD or silicon-based, and we have to move to other types of detectors. And even if we use other types of detectors, the Earth's atmosphere is in the way because there's the water lines in the near infrared, and we have to correct for those or manage to avoid them so that the atmosphere is not opaque at certain wavelengths. And we have installed the SPIRIT camera to try to mitigate these effects. It's installed in our Callisto telescope. It's around, that's the actual camera. It's around this big, and it's mounted on our 1 meter Callisto. And it's a CMOS detector. It's made of InGas, so we avoid the silicon problem. And because InGas it's easier to cool and can be operated at -60 degrees, we can use a liquid chiller, which is this in the middle. So we don't have to use liquid nitrogen or liquid hydrogen to cool it down, which is another challenge that makes near-infrared observations more expensive from the ground. And with SPIRIT, if we look at the range that we want to observe in the near infrared, where silicon ends, InGas we can detect until around 1.6. We try to avoid the water lines as most as we can by using 2 filters. One is our custom ZYJ filter that tries to observe the biggest range, 0.8 to 1.3, of the near infrared while avoiding the large water lines. And then we observe in the H until the InGas stops being effective. So I've mentioned CMOS twice or 3 times already, but I actually haven't told you what it is, which is important. And in our CCDs, we know that every pixel acts as a bucket essentially and collects the electrons, and then they are transferred following an array until our amplifier that takes it to our computer. In a CMOS detector, every pixel is equipped with its own piece of electronics. So every pixel has an amplifier, and it gets turned into voltage that then gets sent to our computer directly. So essentially, we read out all of the pixels simultaneously. This means that we can get a very high readout speed of less than 1 second, or even less than 0.1 seconds. And we use less power, we can get more observations per night. However, because every pixel has its own electronics, there's a higher chance of something going wrong. And we have higher readout noise and higher systematics. So it is a trade-off, you could think, between the space resolution we lose, but with the time resolution that we get from the readout speed. So here's a raw data of SPIRIT. And there are lots of phenomena here that are unique to CMOS and to the infrared. This has been a lot of my work, but for the sake of time, I'm not going to go a lot into detail. Just trust me that it's very difficult, and there's a lot of things going on with bad pixels and thermal glow. And if you want to hear more about the data reduction and the calibration, I'm happy to tell you more about it later or in the questions. So instead, let's look at some results from our observations. If we look at the coldest target on our target list, which is an L5 brown dwarf at 1,900 Kelvin, we get what you can mostly ignore the equation is we just get the contribution from every source of noise. We get, as we expected, that the thermal noise and the readout noise are our main contributors of uncertainty. However, we get around 1 ppt precision, which is better than the precision that we get observing simultaneously with our CCDs. And if we repeat this process for all of the 2022 and 2023 observations, which is 373 observations, we get a 10-minute bin precision of 1 ppt across all our bright and faint stars. We translate this into planetary radius to make it more interesting for the non-observers here. This means that we get rocky planet precision that we would detect at 4 signal to noise higher across all of our temperatures. And in the UCD in particular, we go down to smaller than Earth radii detections with a good signal to noise. If you want to see some actual data, we can zoom in to TRAPPIST-1, and we get a sub-ppt precision on the TRAPPIST-1H transit, which is the shallowest transit of the TRAPPIST-1 group. And just to finish, I will share a couple of discoveries that we've had with SPIRIT so far. This is not a rocky planet, but it is a very interesting mangoes planet. If you're not familiar with mangoes, you should go read about it. It's a very interesting survey. but these are giant planets orbiting very small M dwarfs. And we have used spirit observations on both of them to confirm them. And more recently also the TOI 2407b, which is a Neptune that is in the Neptune desert, and can see in the data compared to the other wavelengths, we achieve similar precision than from our other wavelengths observations. And you see we have a higher scatter, we have a high thermal background from observing in the infrared. However, we have very high cadence, much higher than we can get with our other observations, and this allows us to get really good time resolution. So I'm gonna leave the conclusions here, and if you are a PI and you've managed to find every single spirit, you win a brand new postdoc, because I'm looking for a job. Thank you.
That was fast, amazing. So we have time for questions. Yes, we have one here.
Thanks, Thomas Wilson, University of Warwick. Very interesting talk. I mean, the CMOS results that you're showing here seem, better than the CCD work that you also showed. So that begs the question, are you going to put the CMOS detectors on the other telescopes so that you could combine four to get the four telescopes to achieve an even higher precision?
Yeah, good question. Yeah, so that's the plan. We have another spirit camera that was thinking of installing in another one of the Southern Hemisphere ones. And Mathilde will go in more detail about this in the next one, but there are plans of having a camera that observing both wavelengths as well. So there'll be more on Mathilde's talk.
Cool, thanks.
There is one question here.
Hi, Leon Janssen from Lion Observatory. And so yeah, thanks for your great talk. I was curious, so I think I don't really understand why in this case, like this better time resolution works better for detections compared to like a better spatial resolution. So like, what's the reason why CMOS detectors are better than CCDs in this case?
Well, in particular for transits, we can get better resolution on the limb darkening and radius. And we're using less energy and we can get more exposures per night. So it's a matter of the efficiency and the cadence compensating for what we lose in the resolution. That makes sense?
Yeah.
Yeah.
Thanks.
There was another question up there. Yeah.
Thank you. William Brilliant, University of Cambridge. I was wondering a few slides back, you had a plot of precision versus J magnitude. Why were some of the points jumping way up for certain J magnitudes? Is that random noise or is there a systematic at certain magnitudes?
In here, this
Yeah.
Oh, yes. So we found that the bigger source of unpredicted uncertainty is actually our limitations of our field of view. So we have a very small field of view in this camera. And when the field is very sparse, then we don't get enough comparison stars to correct for atmospheric effects. And we get these points. But this has been mitigated. Yeah.
Thank you.
Jean-Philippe Beaulieu, Paris. I have seen that you have very broad filters that are actually taking a bit of the absorptions of water on the side. I know that it's paranal, so it's fairly dry, but did you try also with some filters that basically would be excluding a bit the water absorption? Because this way, normally you should be able to even push your noise budget further down. That's just a good feeling.
Yeah, thank you. Yes, I didn't mention, but we also have a J filter. And we haven't actually considered making the filters narrower, but there was a code implemented trying to compensate for the precipitable water vapor effects as a post-processing. So we are trying that first.
Okay, let's thank our speaker again. Now we have Francois Boucher telling us about the first rocky worlds revealed by the near-infrared planet searcher, NIRPS.
very much. Fantastic. Hello, good morning. I'm very glad to present you some recent results obtained with NIRPs. I would like to say also that radial velocity techniques is far to be an old-fashioned technique, especially in the near-infrared. So I will show you some recent results using NIRPs, which is a near-infrared spectrograph, which is installed in the on the 3.6 meter telescope. So it joins ARPS in La Silla and is operating in the near-infrared. So, oops, next. Here it is. Yeah. So this project is co-led by René Doyon from Montreal and myself from Geneva Observatory. There is also partner from Portugal, France, Brazil, Spain, and Canada. So the instrument is made with a cryogenic spectrograph, so it's operated under vacuum at very low temperature. It's a link to the telescope with a fiber link, and in order to also to limit, to reduce, to mitigate the modal noise, we use a fiber stretcher and also a double scrambler to guarantee stable, homogeneous beam at the entrance of the spectrograph. On the telescope side, you can see here at the cache-joint focus, what we call the front end, which is equipped with a HEO system. So this is a spectrograph which is fiber-fed, and thanks to a coupling with a HEO system, adaptive optic system, in order to optimize the coupling with a relatively small fiber. We have a fiber of 0.4 arc-second on sky for the high accuracy mode, 0.9 arc-second on sky with the high efficiency mode. So we have two sets of fiber reaching a spectral resolution of 75,000 for high efficiency, 85,000 for high accuracy. We cover YJ band. This is an example of the Proxima spectra obtained with NIRPs. Overall throughput, including everything, close to 13%. We can operate simultaneously with ARPS. We mitigate the modal noise with a fiber stretcher, and also we use the HEO system to scan the entrance of the fiber to be sure to feed all the modes of the fiber. The sun is also observed every day as a star using the solar telescope Helios. This is the typical radial velocity photonoise uncertainty we reach with half an hour exposure on early M in red, in late M's in black. So you see we can reach photonoise limit of 1 meter per second in 30 minutes for H magnitude of 8.2. Oops. So NIRPs allows us to reach a very high intrinsic stability. This is the typical drift of the instrument over one semester. So you see about 4 meters per second and over 100 days. So it means intrinsic drift of only 4 centimeters per second per day, thanks to ultra high stability, thermal stability. The grating temperature is well below 1 millikelvin of stability. Over a week, the Fabry-Perot drift allows to let's say, measure stability at the level of only a few centimeters per second over one night. So it means that, in fact, we do not need any more simultaneous calibration, and we can use a second fiber to monitor the sky, and especially the OH lines, which contaminate the spectra. For the wavelength solution, for the long-term stability, we combine hollow cathode lamp with Fabry-Perot to reach a few tens of centimeters of uncertainty on the 0 point of the instrument. So NIRPs, we started in April 2023 a large program, a guaranteed time observing program with a total of 725 nights over 5 years, with several key programs, and I will show you a recent result from the blind radial velocity search for exoplanet around M-Dwarf, and also a radial velocity follow-up of a transiting planet around M-Dwarf, part of these two main programs. So one example, we revisited the well-known Proxima system. So we have more than 2 years of data, and Proxima is the closest star to the sun. It's a late M, faint in V, but very bright in H band. And with NIRPs only, we derive the semi-amplitude with about 10 sigma accuracy. The dispersion of the residual are at the level of 80 centimeters per second. So this is the first near-infrared spectrograph reaching this kind of accuracy. Combining with other ARPS espresso data, we confirm also the second planet at 5 days, Proxima D, with, it's marginal with NIRPs, but when we combine everything, we have a clear signal of Proxima D, which is 26 Earth masses at 5 days period. And we exclude Proxima C, which was announced with a 1,900 days period. We also revisited JG3090, which is a early M2 draft with a slightly fainter. So the transiting planet, which is a sub-Neptune, is characterized with a sum amplitude of 3 meters per second. It corresponds to a mass of 4.5 Earth masses. And we detected also a non-transiting planet relatively close to the rotation period of the star. So using multidimensional GP, we were able to really characterize this planet without being too much affected by the stellar rotation. And we also propose a third candidate, but it's just with still some uncertainties on the semi-amplitude. This paper is submitted by Avidan, so we follow up this test candidate 4542, which is an ultra short period super Earth candidate with a radius of 1.1 Earth ready at 0.3 days around the late M, relatively faint. And you can see also here the gain of NIRPs with respect to ARPS. So clearly for this kind of target, mid-M, late M, there is a significant gain using NIRPs. So the detection is at 4 sigma, so there is still room to improve the mass and the density of this planet. Presently, it's like between a Earth-like composition and the iron-rich composition in this diagram, combining all the known ultra-short period super-Earth. Still have time. Another result, we revisited this planetary system, GL581, and combining archival data from ARPS and the new 2 years of observation with both ARPS and NIRPs, we were able to update the parameters of this 3-planet system to exclude other claim candidates, to have a deeper analysis of the impact of stellar activity in both the visible and the near-infrared. And for these stars, we were able to, let's say, refine the rotation period of the star, which is a long period, and 133 days. And for this star, we see that the signal of activity on the near-infrared is larger than the optical, which was a bit surprising. It's not the case for a shorter rotation period. And then we were able also to fix upper limit in terms of mass of planet within the habitable zone between 0.8 and 1.4 Earth masses. We also revisited the famous TRAPPIST-1 system with both Spirou and NIRPs. So Spirou was trying also to push in terms of radial velocity precision, but had to face to some strong systematic of the instrument. NIRPs is much more stable, but here we have larger error bar because the goal was to probe the outer part of the system. But when combining everything, we were able to put some constraint on the system, and specifically, so we are not able to derive the mass of individual planets, but assuming that the relative masses derived from TTVs are correct, we combine the radial velocity planetary signal in order to make a global modeling of this system, assuming that the mass ratio or semi-amplitude ratio from TTV are correct. So combining Spiro and NIRPs, we were able to confirm in radial velocity the amplitude of planet B, assuming combining the impact, the effect of all the planets in the system. And it's well in agreement with the TTV determination. And we put also upper limit in mass for outer companions up to Saturn mass object at 600 days, on Jupiter-like planet at a few years. Thank you very much. So don't forget to listen to Drew. This afternoon, we will also present some NIRS results, and come to us. There is a few of us coming from the science team, which can answer to your question. Thank you very much.
Great. Questions for Francois? Yes, there is one here.
William Brilliant, University of Cambridge. I was wondering if it's ever beneficial to observe with both NURBS and HARPS simultaneously, and that sort of gives you a really wide spectral range to look for an RV drift. Is that ever done?
Yeah. So it's typically the default mode. So we observe almost every time with HARPS on NIRS. For late M, the HARPS contribution is very small. Sure. So it does not really make sense, but it comes for free. For early and mid M, for early M, there is a similar contribution. So we can really increase, let's say, radial velocity contents combining both instruments. Also, I didn't mention, because we have also the Work Package 3 program linked to atmospheric characterization. And here we can really, for atmospheric characterization, combine the determination of chemical species from in the optical and near prime, which is really again.
Did you observe with NIRPS late M or brown dwarf spectroscopic binaries, double line spectroscopic binaries?
No, during commissioning, yes, we observed the famous L-DRAF binaries. I don't remember the name, but yeah. So I mean, no, it was it's a fan target. I think it's 17 in V at least. So it's at low SNR. But yeah, yes, we did some tests.
And final question.
Thomas Wilson, University of Warwick. At the end of the 5 years for the NIRPS GTO, how many targets do you reckon you'll have characterized? Is this going to be like demographic levels of planetary systems that we can then go ahead and analyze, or yeah, what are kind of numbers that you're looking at?
Yeah, so it depends on the program. So for Work Package 1, it's really it's a census of nearby star up to 7 or 10 parsec. So this is a plan, yes, to cover as much as possible in the nearby vicinity of the sun. Work package for a test follow-up. No, we follow several tens of targets, but I'm not sure. I mean, yes, it will help increasing the mass radius diagram of transiting planets, especially around M-DRAF. And yes, there's a goal for atmospheric characterization. There is indeed a census. So with several tens of planets for helium and evaporation processes there.
Very cool, thanks.
Okay, let's thank Francois again. And now we have Mathilde Timmermans telling us an update on the Speculoos survey.
Thank you. Yes, how's it going? So hi everyone. I'm Mathilde. I'm a postdoc at the University of Birmingham, and oops, there we go. And yeah, I'm here to present an update on the Speculoos survey. Claudia has already introduced this, but I just want to remind everyone why we care about these ultra cool star systems. Well, first of all, they're really cold. And that means their habitable zone is a lot closer, so it's easier to detect habitable zone planets, right? And because of their very small size, they create very large transit depths for Earth-like planets. And it also has advantages in the case of atmospheres because, well, they peak in infrared and the transmission features are large, and it requires less telescope time. So basically, they are great targets for the JWST. And this is basically what motivates our science case. So we focus on the search for transiting rocky planets in the habitable zone, if possible, that are well suited for atmospheric characterization with the JWST. Our second science case is also to to measure occurrence rates of planets orbiting ultra-cold stars. So I will describe a bit the target list and the observing strategy, but all of that can be found in great detail in the Sebastian et al. 2020 paper. And yeah, so I invite you to have a look. So we based ourselves off of a very large list of M and L dwarf stars. So it's a catalog of over 14,000 stars that it's a volume limited sample. So we are looking within 40 parsecs. And from this catalog, we constructed 3 different programs. So the first one is exactly trying to find Earth-like planets that are amenable for characterization with the JWST. So how did we find our targets? Well, we calculated the signal-to-noise ratio that we would get for 200 hours of observations with NIRSpec. And we decided to put the limit at an SNR of 4 because that's where we estimated that we would get good constraints on the atmospheres. The purple star there is TRAPPIST-1, just to give you an idea. For the second program, we were looking at the synergy between TESS and speculus. So the idea was to look at transit-like signals that would be low signal-to-noise ratio in TESS and see how much better we could do in terms of precision, but as well as looking for additional planets in the system. So we did a similar exercise where we calculated the signal-to-noise ratio that we would get in 2 test sectors, and we put the limit at an SNR of 5 in this case. And finally, our third program includes all of the objects that we have in the catalog that are later or equal to an M6 spectral type. And obviously, they shouldn't be already included in program 1 and program 2. So in total, we have a little over 1,700 stars with about 20% of our targets that are program 1, which is the program that we focused on thanks to the launch of JWST. And we have about 10% of program 2 and about 70% of program 3. So our observing strategy was based on the fact that we wanted to detect at least one transit of a temperate planet orbiting a UCD. So that would put the period at about 6 days or less. So in order to figure out exactly how we were going to monitor those stars, we had a look at the phase coverage that we would get for a range of periods. So here we had a random speculus target that we observed for 134 hours. And with those nights that we observed, we actually have a coverage of 80% for a period of 4.7 days. So we did this calculation for a whole range of periods. And we did that for all of our targets. So this is the number of hours that we observed our targets. The red dots correspond to real observations, so real targets that we observed. And this was the, I'm back. Yes. So this was the coverage that we looked at for a period of 6 days. And we saw that we actually have an 80% coverage for 800 hours of observation. So this is what we decided for programs 2 and 3. Basically, we said, okay, we're going to get 100 hours on each of these targets. for program 1, we decided to extend this to planets that would be in the habitable zone of their host stars. So that is going up to periods between 8 and 10 days. And so we decided on 200 hours. The Speculoos consortium is very big. And I just wanted to give you a little timeline of what happened. So Claudia already mentioned our telescopes are 1 meter class telescopes. They're all twins of each other. And we have we have 6 actually right now. So we started the survey in 2015 with a prototype survey on the TRAPPIST South telescope, which actually led to the discovery of TRAPPIST-1. Then in 2017 and 18, we populated the Speculoos Southern Observatory. And it was in 2019 that we started to observe also in the north. So that meant that we built Artemis in the Speculoos Northern Observatory, which is in Teide Observatory in Tenerife. And then we also have Saint-X that joined the consortium, which is also a twin telescope that is in Mexico. In 2022, obviously, we installed Spirit. Claudia mentioned that. And I'm very happy to report that we have the commissioning of our second telescope in the Speculoos Northern Observatory that will happen this summer. And we're really excited about it because it's going to be a dual photometer. So we'll have a Spirit-like camera on the one hand and an optical one on the other. So that will allow us to do a lot of cool stuff. So I just wanted to give you a bit of an idea as to where we are right now. Like I said, we put the priority on program 1 targets. Oh, I got that. Okay. So we've actually observed more than 250 program 1 targets, and that means that we're slowly reaching the end of that. So we've actually even started to observe in recent years targets of the other programs. So just a quick word on the expected yield. This is again in the Sebastian et al. 2020 paper. So we calculated what we would expect for discoveries, and that was basically between 5 and 20 planets, depending on the program. So I just wanted to mention our discoveries. Obviously, TRAPPIST-1, I won't describe it, everybody knows it. But yeah, TRAPPIST-1 is actually Speculoos-1. And a little fun thing that I wanted to add was the very first transit that we got with TRAPPIST South. That dates back to 2015. Obviously, TRAPPIST-1 is the system that has been observed the most with JWST, both in transmission and emission. Then we also published the discovery of the LP890-9 system, which is also called Speculoos-2. And that one has also been observed with JWST in transmission. That was very recent, so I'm really looking forward to the results. And then finally, the latest addition to the Speculoos systems is Speculoos-3. It's an ultra short period planet, so it's actually really good for emission with the JWST. So I will leave you with this complete timeline and take any questions. Thank you.
Great. Are there questions for Mathilde? Well, I can start with one. I was wondering if in all this timeline, there was a revision of the observational strategy and there was something that you learned that you can share with other people thinking on doing surveys, something you would have done differently or something you are going to change for the new telescopes?
So we're going to keep the current observing strategy with the new telescope, but there is certainly a lot of discussion about the strategy as we go along, especially now that we've finished with program 1, we can actually get some lessons from that for the other programs. But yeah, so far we're going with that still.
Okay, then let's thank Mathilde again. There any announcements? Okay, we have one announcement before lunch, and then we'll get lunch, and we are back at 1:30. So.
Use the hand mic.
Yeah, just real quick. I just want to announce that tonight we will have a karaoke. So please, if you would like to rock us like a hurricane, join us tonight at the Drie Gezusters. It's the largest pub in Europe. It's a wonderful interior, and we have our own private room inside. It's at the Grote Markt, which was a big square in front, pretty close to where we had the dinner last night. It's difficult to miss it. You need to take the rightmost entrance and then immediately go to the left so you can see the stairs. Walk up the stairs a bit to the back, and there will be our private room. It starts at 8, and it will go on until, well, when we're all kind of screaming our voices out. And please bring your conference badge, because we will have a security guard in the entrance that will ask you for your badge. So yeah, please join us all tonight and enjoy your lunch.
Combine the experiments, the models, and the observations in order to better understand the chemistry of central exoplanets. And today I will focus my talk on an exoplanet already heard about during this conference, which is KT-8. It is a sub-Neptune, which is orbiting an F-dwarf star, so a relatively small and small star, and it has an equilibrium temperature around 300 Kelvin. And I'm interested in this planet because it's one of the few temperate exoplanets, so let's say below 400 Kelvin, for which we have detected and characterized an atmosphere. And this was thanks to the technique of the transit spectroscopy we already heard about. So this was supposed to be a video, but I explained you the principle really quickly. So when you observe the light of the star coming towards you, in different wavelengths, when the planet orbits in front of the Earth, it will block the light with different efficiencies depending on the wavelength because of the content in the atmosphere. And when you combine all the wavelengths you observe, you obtain a whole transmission spectrum in which you see the absorption bands that are characteristic of the content of the atmosphere of the planet. And thanks to these observations, we know that K2-18b has an atmosphere dominated in H2, and we support the presence of some carbon periodization, such as methane and carbon dioxide. So that's already exciting news. But the observations remains hotly debated. We don't really have robust constraints about the proportion of these species, and we don't really have reliable information about other molecules. So that's what we are going to try to explore in deeper details in this talk. And to do so, we will try to simulate in the lab the atmosphere of the planet. And what we are going to simulate exactly is the upper layer of the atmosphere. So it's at low pressure and temperature. And it's where you have a UV flux coming from especially from the star, that will drive and all of the real photochemistry. And that's these processes we want to simulate in the lab. And to do so, we are using a reactor in which we are going to inject some gas mixtures that are meant to be the analogs of the atmosphere. So it's mixtures dominated with H2 with various proportions of methane, carbon dioxide, and carbon monoxide. So where we want to simulate a wide range of possible atmospheres for our temperate exoplanets. This mixture is injected at 1 millibar and 300 Kelvin, so it's more or less the pressure and temperature conditions you find in these upper layers of the atmosphere when you have the UV flux. And we use an energy source, so here is a good map, to reproduce the stellar irradiation, to simulate this irradiation. So that it drives the ground chemistry. And now we want to track in our setup
the evolution of this chemistry to do so. We are using different techniques. So like the GWT, we are using infrared spectroscopy. So as I've explained before, in infrared, every molecule will absorb at a very specific wavelength. So you can find like the fingerprint of the molecule in the spectrum to identify the compounds. And we're using a complementary technique, which is mass spectrometry. So the principle is that every of your molecule will be dissociated in specific mass charge ratio. So you will obtain a specific fragmentation patterns for every one of your molecules. And so in your spectra, once again, you will try to identify the fingerprints of your molecules to identify which molecules are present or not. And to complete this analytical diagnosis, we also want to simulate what is happening inside our reactor. And to do so, we're using a zero-nucleate models. And these models will help us to have ideas about the abundances of our species with their also main destruction and formation pathways. So with all these techniques, what do we observe in our experiments? So there are several compounds, and I will focus my talk on two main family compounds. The first one being the reduced organics. So here, what we see is a mass spectrum in the initial state. So we have only injected 95% of H2 and 5% of methane. And then we turn on the plasma, so we irradiate the mixture and inject all of the equilibrium chemistry. And then we get the spectra. And what we see is that there are many peaks that appear in the spectra, and these peaks are chains composed of carbon and isotopes that we call hydrocarbons. And we found up to 6 carbon atoms in this chain. So we highlight here that we are driving a really kind of complex chemistry. With the 0D model, we can access to these final abundances in those mixtures. And quite simply, what can we see? We see that in the methane-rich mixtures, this organic growth is the most efficient. The formation of this hydrocarbon is really limited in the carbon dioxide pure mixture, so where you only have H2 and CO2. And it's quite an intermediate in the carbon monoxide case. And if you want to understand why in more detail, you can come and talk to me after, or you can read my paper that for the latest version is available on archives this morning and will be published in Astronomy and Astrophysics Study. And now let's see the second main family of compounds, which are the oxidized organics. So by combining both the mass spectrometry features and the infrared features, we robustly identify the formation of methanol and formaldehyde and maybe of the beta-acetaldehyde. These compounds are of great interest. They are known to be precursors in the biological chemistry. And in our mixtures, with our 0D model, we predict that in the carbon monoxide pure mixtures, their efficiency will be greater than in the carbon dioxide pure mixtures. But as soon as you add methane in these mixtures, you greatly increase this abundance by several orders of magnitude. And in this case, where you combine methane with an oxidized reactor, this time it's in the CO2-rich mixtures that you have a better efficiency than in the CO mixtures. And once again, if you want to learn more about the chemical details, the formation and destruction pathways of this molecule, you can read the paper to see all the chemical networks of entropy. So, experiments, we've highlighted a number of compounds. So we also have detected a lot of water vapor, for example. But the two main families with the highlighted view here are the hydrocarbons, so acetylene, ethylene, and methane, and oxidized organic, methanol, and formaldehyde. And now we can ask ourselves if we could ever detect these kind of molecules in our atmosphere. To answer this question, we try to fit the observations with a 1D out of equilibrium model. So from the observations, I'll spare you the details, but with the model, we try to fit the best possible the observations. And the information we got from the 1D model that we can access to the possible abundances of our molecules, of a wide range of molecules. And if we overplot the detection limit of our molecule, then let's see what it gives us. So for the oxidized organics, the detection limit that was predicted for the GWST is around 1. And you see that for formaldehyde and methanol, their predicted abundances in the K2-18P atmosphere should be below the detection limit. So we don't expect them to be detected. But in other atmospheres with higher proportions of carbon monoxide or carbon dioxide, these molecules could be produced in higher abundances and maybe overcome these detection limits. And also there is, we should explore maybe their detectability with the next generation instruments on the ELT, which will have higher resolutions. And for the hydrocarbon space, so you see that we have several cases where the abundances of the hydrocarbons could reach higher abundances than this detection limit. So they could be detectable, and maybe we have already detected some. Because there are several infrared features that were attributed by Madhusudan to GMS or GMTS. But Lou Little reanalyzed this data a few months ago and proposed that the fitting of these infrared features could be as well attributed to some hydrocarbons such as pave. So maybe we are already at one feature that is corresponding with this molecule. So to have a quite simplified sum up scheme, the observations give us some entry parameters for the models and the experiments. The models help us to interpret the observations and the experiments. And the experiments give us constraints and ideas of what to look at in the models and the experiments. So it's the interaction between these three fields that is really important and that helps us to have robust and stronger ideas about what the chemistry in the temperate exoplanets can look like. And I thank you for your attention. And I mentioned that my PhD is called Reaching its End in Humans. I love exoplanets, I love experiments, I love astrobiology, among other things. So if you have any projects that combine one or several of these aspects, I will be really happy to discuss with you.
Inga Kamp, University of Groningen. This is really super cool to see these experiments. So I was wondering, the one thing you left out is a comparison with the 0D photochemistry model. So can you say a little bit more? Out of equilibrium is a bit vague. So is it kind of very easy and steady state, or does it depend simply on the carbon to oxygen that you put in your initial gas, or what is driving this chemistry?
So, Edward Barrier, do you observe any hazes or longer chain has precursor? Sorry for the pronunciation.
yeah, I suppose that I should reach higher carbon content, so higher methane proportion, for example, to observe this kind of hazes.
Désolé, ça a coupé à la fin.
All right, can you guys hear me now? Even better. All right, so yeah, I'm Drew Weiserman. I'm a PhD student at McMaster University, and I want to present my comparisons of rocky planet and host star chemistry for a sample of M-dwarfs using the NIRP spectrograph. So it all starts with the radius valley. I figured I'd be creative and use a different radius valley plot this time. So around sun-like stars, we have a pretty good idea of what's going on with the radius valley. Around those FGK stars, we're reasonably confident that the main cause of the radius valley, its main driver, is some sort of thermally driven atmospheric escape process. But around M-dwarfs, the cause isn't quite so clear. The quantitative shape of the radius valley, its slope in radius period space, and how relatively filled the radius valley is quantitatively different than around sun-like stars, requiring a different formation process to explain. Around those M-dwarfs, it looks like the radius valley is consistent with a process called water-rich formation, where those planets around the radius valley form with a whole bunch of volatiles as part of the formation process, as the radius valley's primary cause. We have some evidence of this, like I said, the shape of the radius valley, for example, but it'd help if we can get direct observational evidence of this. And one way we can do that is by looking at the core mass fractions, or CMFs, of hot rocky planets. Normally, when you're calculating the core mass fraction of a rocky planet, you just take its mass and radius, and you do some interior structure modeling to fit for the fraction of the mass of the planet's mass that's in that mostly iron core. And if you do that on really hot planets below the radius valley, you can be reasonably confident the planets have no thick hydrogen atmosphere, no surface water, so there's only the core and the mantle, making this not necessarily a degenerate problem. But there's another way you can infer the composition of these planets too, and that's by looking at their stars. Stars and planets form from the same primordial cloud of material, so oftentimes it seems a reasonable assumption that the planets and the stars should have similar ratios of refractory elements. And so by getting abundances of a host star, you can look at the planet and infer what the composition of the planet, quote unquote, should be. And this gives you two different estimates of the core mass fraction, which we'll call the planetary and the stellar CMF respectively. And having two different estimates of the CMF lets you compare them, which can tell you a lot about what sort of processes might be going on in those planets. For example, if those two CMF estimates are equal, then that tells you that yes, the planets do have similar refractory abundance ratios to their stars, and that seems to imply there's no weird enhancement or depletion processes going on in those planets. But if the two estimates are different, then you need to figure out why. If the planetary CMFs are bigger and the stellar CMFs are larger, then that tells you these planets have more massive cores than their stars would imply. And if we were to see that, then we might interpret that as maybe like mantle stripping caused by giant impacts, for example. But if the planetary CMFs are smaller than the stellar CMFs, then what's going on there? That seems to imply the planets have smaller cores than expected, and we don't really know how a planet could be iron depleted. Like, how do you get the iron out of the mantle? It doesn't really make sense. So that seems to imply that there has to be something else inside these planets, something less dense that's causing this difference, like water. Recent theory suggests that for super-Earths, not just sub-Neptunes, but super-Earths, water can be sequestered deep in the interior of these planets, the mantles and cores, which can inflate these planets. And if you inflate these planets, then you're decreasing the bulk density of these planets, meaning you're deflating the measured planetary CMF. But there's a bit of a wrinkle there. If there's a lot of water in the mantle, and especially if there's water sequestered inside the core, that water can't really get there after the formation process. That water would have had to been there throughout the whole formation stage, which is just what water-rich formation is, if there's a lot of water during formation. So if we see that on a population level, the planetary CMFs are smaller than the stellar CMFs, we can interpret that as due to the presence of volatiles sequestered in these planets. Now, this sort of comparison of rocky planet and host star chemistry has been done before, but primarily on FGK stars and not M dwarfs, mainly because getting stellar abundances for M dwarfs is a pain in the butt. But we do it here on a sample of exclusively M dwarf planets, which really lets us probe how those planetary formation processes differ between FGK stars and M dwarfs. So for the last 2 years, I've been leading a program within the NIRPS consortium called the CMF subprogram to do exactly this. We've been getting a whole bunch of radial velocities, probably too many, radial velocities using a NIRPS spectrograph to try to constrain the masses of 3 hot rocky super-Earths to the 10% level, GJ1132b, GJ1252b, and LTT3780b. From there, we can also get the spectra of those stars by taking those same spectra that we get radial velocities from, and from those spectra and from those masses, we can get both CMF estimates and compare them. And then because 3 planets isn't enough to do a whole population sample, we go ahead and get spectra for 6 other planets too, that already have reasonably precise masses from the literature, but whose stellar abundances can still be constrained. So in the interest of time, I'm going to skip past all the radial velocity modeling and analysis and just go straight to the radial velocities on the plots. So here you can see a phase-folded plot of our radial velocities for GJ1132b with a stellar activity signal removed. And you can see our mass right up there. And I would say that's pretty precise. We did indeed hit the 10% precision goal that we were hoping for. And there's GJ1252b. We did just barely miss out on that 10% mass precision we were hoping for, but not the end of the world. And LTT3780b, another paper published like 150 Maroon X radial velocities while we were observing, but hey, just means we can do way better than that 10% precision we were hoping for. So now that we have those masses and we get radii from literature photometry, we can go ahead and calculate our planetary CMFs. To do that, we use the super-Earth interior structure model, which I have been told by the interior structure modeling people is quote-unquote good enough. And we can go ahead and essentially, given the masses and radii that we calculate, fit for the core mass fraction of the planets that best matches those results. And you can see our posteriors right over here. We find that the core mass fractions for our planets tend to span a range of CMFs, either being consistent with 0, like L90 at 59C, or TY270b right there, whether or not a coreless planet is actually possible, or some that appear to have a more Earth-like core mass fraction of like 1/3, and everywhere in between. Sorry to Super Mercury fans in the crowd, we do not see any Super Mercuries in our sample. But now that we have that, we need our other CMF estimate, our stellar CMF. And to get that, we need stellar abundances. So we develop a new spectral synthesis routine to get M dwarf abundances from near IR spectra. I'm not going to get too into detail here, because first of all, if I start talking about it, I will not stop. And secondly, a paper by my second author, Gromick et al., is coming out very soon. And you can read about the routine a lot more detailed there. But suffice it to say, we have all sorts of cool tips and tricks to try to make the best of M dwarf spectra, which can have a lot of blended and contaminated lines that you really don't want to deal with. So we go ahead and calculate iron, magnesium, silicon, and sometimes titanium abundances for all of our stars. And then we can go ahead and feed those abundances back into super-Earth, that same interior structure model we were using before. Except instead of feeding it a mass and radius and it trying to fit for the core mass fraction of the planet, we can feed it those stellar abundances, and it tries to fit for the composition of the planet that best matches the refractory abundance ratios of the star. And we get this. You can see the posteriors for our CMFs up here, planetary in orange and stellar in blue. And I don't know about you guys, but it sure looks to me like the planetary CMFs tend to be smaller than the stellar CMFs. Even though there's a lot of overlap in the posteriors for each individual planet, at a population level, there's a clear distinction. Like we said earlier, if we see that difference, we can interpret that, that underdensity for the planets as being due to the presence of volatiles on or in these planets, and this looks like evidence of that. But of course, you do want to ask how much water is actually necessary to cause that underdensity. Because if you need like a 40 or 50% water mass fraction to explain it, then maybe something else has to be going on, because that's not quite a plausible scenario. So to do that, we figure the water in these planets can be in one of two different places. Either differentiated on the surface of the planet or sequestered inside the interior. We suspect the latter is more likely because these are hot planets, and a lot of these have just been shown to have no atmosphere, no supercritical steam atmosphere, but better safe than sorry. So we go ahead and get interior structure models that account for both those scenarios. Models from Aguachine et al. 2021 for this differentiated water, and from Low and Dorn et al. 2024 for those models with water sequestration. And we go ahead and interpolate through them to find what water mass fraction would be necessary to explain the difference between those core mass fractions. And we find you don't actually need a lot of water to explain those differences that we measured before. We find that water mass fractions consistent with like 1% could explain the discrepancy between those two CMF estimates that we find before. Importantly, that number doesn't really change much whether or not the water is differentiated or sequestered. So the mass and radius alone might not be enough to distinguish between where the water could be on or in these planets, but we do find that the amount of water required to explain the difference between the CMFs is is consistent with caps in the water mass fraction of a few percent that planetary formation evolution models seem to imply are plausible. And so yeah, the interest of time, I'm going to go ahead and wrap up there. We can go ahead and measure the core mass fractions of our hot rocky planets. And by doing that, we can learn more about what the composition of these planets might be. We do that in a sample of M dwarfs using a NIRP spectrograph. And we find that these planets seem to have systematic underdensities, which we attribute to the presence of water on or in these planets. Thank you. Anybody have any questions?
Thank you, Drew, for a great talk. Oh, there are many questions. Let's start somewhere completely in the back. I guess in the back it's most difficult to get a question in. So this is fine. Yep.
Thank you for the great talk. James Rogers, University of Cambridge. Has this analysis been done on a sample of sun-like stars?
Yes, so a few different studies have tried to do this, but with sun-like stars. There's Adebekian et al. 2021. There's Brinkman et al. 2024 and 2025, which even use the same interior structure models as this. And they tend to find not the systematic underdensity, but they tend to find a correlation, a relatively strong correlation between the two CMF estimates. The exact strength definitely differs on the paper, but none of them seem to find the systematic underdensity that we observe here.
So the conclusion is that no extra sequestered water is required for the
Correct. Yeah.
Thanks.
Other questions? Here in front, here.
Hello. Okay. Hi. Thanks, Claire Guillaume, UTH Zurich. How do you distinguish between water and another lighter component, for example, the sulfur-rich core, like we saw that in the Pluto white dwarf sample?
So that's a really good question. We don't actually do that here. All that we find is that these planets do tend to be systematically underdense. We're interpreting that as due to the presence of something like water, just because of our a priori assumptions about how planets form around here. But theoretically, yes, this underdensity could be caused by some sort of other light material. We just think water happens to be the most likely in these planets based on what we know about them.
Thanks.
There's a final question here. Yep.
Okay, Thomas Wilson, University of Warwick. I actually have two questions, but the first one is pretty, well, hopefully straightforward. What is the stellar CMF of TRAPPIST-1?
I don't know, it's not my sample.
Right.
I can
And
calculate it later. This task.
I'm very curious about that. And I think I see at least one system with two planets in there. So can you comment on the difference in the planetary and stellar CMF for, is it the L9859 system? Yeah.
Yeah. So L9859b is my single least favorite planet in this entire sample. It is the outlier in every way, shape, and form. For starters, it's the only one where we don't really see that systematic underdensity. And if you look over here, it's that one huge outlier in mass and radius space. I don't quite know why this one doesn't show the same anomalous underdensity. I have a few ideas. It could just be because of the mass and radius. It could be because this planet is one that's thought to potentially be suitable for volcanism, so it could maybe be just a lot better at outgassing all the material that we sequestered. I don't really know. That's for people other than me to figure out. But if you do look, we have the exact same posteriors for the stellar CMFs. L9859C is well behaved. L9859B is really not well behaved. I wish I had never seen this planet in the first place.
Okay, let's thank Drew again. We have to move on. Okay, our next speaker is Sudeshna Borosaikia from the University of Vienna. Titan as a testbed for rocky planet atmospheres. Go ahead.
Thank you. Yeah, can people hear me okay? Yeah, all right. Yeah, thanks very much. So here, hopefully I can convince you that it's worth revisiting Titan, although we have observed this for decades and decades. And my talk is going to, okay, so why Titan? Although it's a moon of Saturn, Titan is a very interesting case for rocky exoplanets, particularly Earth-like nitrogen-rich atmospheres, because although it's nitrogen-rich, it has a very different atmospheric property, and perhaps that can also help us tell a bit about exoplanets. So Titan has been extensively studied, as I mentioned, and the Cassini-Huygens mission has actually really changed our understanding of Titan's atmosphere. So if we look at the upper part of the atmosphere, this is where most of my talk is going to focus on. So we see that the stellar light, in this case, only the UV part of the light is shown, but it's also the X-ray component as well, that has a dramatic influence on the temperature structure, as you see here. And in addition to that, it's also on the chemistry itself, because Titan has nitrogen and methane chemistry. And this interaction with the starlight, and I'll talk about how, leads to the formation of these aerosol particles, the photochemically produced haze layer, and also it has consequences for the lower atmosphere as well. Now, as you can see at the top, there is also a question mark around escape, because we also want to know whether atmospheric gases are retained or not under different conditions. So this is where I was asking myself, when I was looking at this review by Sarah Hurst, is there a self-consistent model of Titan's upper atmosphere, and what can it tell us about the feedback between temperature and chemistry? And can we reproduce the observations of Titan as seen by Cassini? And the next question, of course, naturally comes from that simulation would be that, is there any way that we can constrain the methane escape from such a self-consistent model? So let's dive in then, what actually is happening here. So, so this is just my, as a stellar star-planet interaction upper atmosphere person, what happens in the interior of a Titan-like planet. So what happens here is that we know for Titan that ammonia and methane outgassing has led to the formation of the atmosphere that we see today. But this atmosphere is shaped by the incoming high-energy radiation of the sun in X-rays and ultraviolet that leads to the different processes here. Some of them include photochemistry, photoionization, then you have photochemical hazes that we mentioned, and also atmospheric heating, because the starlight also directly heats the atmosphere, so has an impact on the temperature structure. And then a question mark here, is there escape, significant escape of methane and Titan? And addition to that, the temperature itself and the chemistry is also impacted by radiative cooling, because when you have atoms and molecules, they also produce thermal emission, and that takes away heat from the atmosphere. And when you are looking at the atmosphere like that, we are also thinking about vertical transport also. So all of these together shape the atmosphere of Titan, specifically the upper part of the atmosphere, potentially the atmosphere that we can observe in Titan-like exoplanets. Okay, so when I wanted to do this study, I looked around and I thought, okay, we have atmospheric models which are self-consistent that can give you pressure, temperature, structure, and chemistry at the same time simultaneously. But one such model would be the compote model. And this is a model that is a 1D radiative model. As you can see, this is the simulation domain. You can set a lower boundary anywhere arbitrarily. It's a user's choice practically. And then if you look at the top, then what happens is that the code calculates the exobase dynamically. So you can actually then see how the radiation is that impacting the chemistry and the temperature. Now, this model was developed at the University of Vienna by Colin Johnston, but this was a specifically Earth-centric model and also Venus as well. So it was dominantly for nitrogen and carbon dioxide-rich atmosphere. So we can't really do Titan with that kind of a model. So we had to, in this case, there is a paper coming out that is currently under review. What I did was I looked into what is needed to simulate Titan using such a model. We need atmospheric chemistry, we need to have a large chemical network that involves methane. And we also need to look at the radiative transfer and look at what kind of emitting molecules, and in this case, methane-bearing molecules, or in fact, hydrogen cyanide, which is important for Titan, as we know, we need to include those processes as well. So this is how we start a simulation. We calculate the temperature structure by solving the energy balance equation, which actually includes contribution from the X-ray, ultraviolet, and infrared heating. We also have chemical heating in this case. We have thermal conduction, radiative cooling by hydrogen cyanide and methane. And when it comes to the chemical network, we actually have around 900 chemical reactions, which include thermal and photochemical reactions. And once we have a steady state simulation, then we can actually also use simple prescriptions to calculate the thermal genes escape from this atmospheric model. So diving straight into some results. So this plot shows here the current knowledge of Titan's thermal structure quite high up in the atmosphere, because I wanted to avoid the haze layers here. Thank you. So since I wanted to avoid the haze layers, I kept it at around 400, 450 kilometers, which is the thermosphere of Titan. And what we see from different observations from Cassini and also from ALMA, the ALMA observations are the circle and square markers here, we see that there is a bit of disagreement between the different observations. But for those of us who are used to exoplanet observations and such, we were like, what is 30 to 40 Kelvin, right? So, but at the same time, for chemistry, does that matter? So how do we do then in terms of simulations? In terms of simulations, so these are some of our models. So I ran 4 models, and the only difference between model A and B, C, and D is that the vertical transport, because we cannot really determine eddy diffusion for first principles. So we actually used few different prescriptions of eddy diffusion profile. And because of the choice of eddy diffusion, we do see small differences between the models, but overall the models do agree with what we currently know from observations. Okay, so we got the temperature structure, and from the same set of simulations, we should also now get the chemistry as well. So here I show the chemistry in terms of the number density of nitrogen, which is the dominant atmospheric gas, together with the second most dominant gas, which is methane. And again, the solid lines are our models, and the open symbols in black are observations. We have observations going all the way down to our simulation domain from Cassini for methane, which do show strong agreement with our models. And nitrogen, on the other hand, in this particular atmospheric domain only was directly measured here at the top part of the atmosphere. So nonetheless, I think we do have good agreement here. But for exoplanets, we probably also want to know what kind of abundances would we get from these kind of models, and how do the abundances actually agree with observations. So coming to methane, because methane is interesting for many reasons. So this is actually a result from Cassini in the 2008 from Yale et al., where they detected quite a high abundance of methane in the atmosphere, specifically at the top. As you can see, it can be up to 10% or so. And the question came, why is there such strong methane presence at the top of the atmosphere? And one of the arguments that was brought forward back in the time was that perhaps methane is escaping at a very high rate, and that's why the question mark around methane, or perhaps there is diffusion that is very strong in this atmosphere. And so how does our model do actually? How does COMPOT does in this case? So these are again the methane abundances from our simulations. And as you can see, there is quite strong agreement between these models and the observations, and they just overlap each other. We are not fitting anything. I'm just plotting what our self-consistent simulations give us. And in here, of course, this model D, we do see slight differences. But again, this is also the model for which we have probably unrealistic level of eddy diffusion as well. And now the question comes, if indeed our observations do agree with, our models do agree with observations, how does the escape rate actually look like for such an atmospheric model? And for us, for models A to C, these models, we do not detect any methane escape, and we only detect methane escape for model E, which is our strong eddy diffusion case, and that too, it's very low. As you can imagine, 2 times 10 to the power minus 4 grams per second is like losing 1 grain of sand every 5 minutes or so, something like that. Okay, so then the last slide before I come to my conclusion. So we also looked at other minor hydrocarbons, and of course, because it's a complex model, which has a lot of physics and chemistry in it, we see different levels of agreement between the different species. So when it comes to hydrogen cyanide, we see strong agreement with observations. So does in terms of C2H4. But when it comes to C2H2, we do see that there is quite a bit of discrepancy between our model and observations, and sometimes perhaps also between observations as well. So where do we go from here? So to summarize, what we did here in this work is actually look at the top of the atmosphere and come up with a self-consistent calculation of its thermal structure and the chemistry from the single simulation. And what we see here is that our results broadly agree with observations, and we do not actually detect any significant escape of methane from Titan. which probably has consequences for the methane budget. And since we don't really tune our model to Titan and we calculate everything from first principles, then we expect it to have a good scalability to exoplanets. And finally, in the future, we would, in the future, we would like to move it to deeper down in the atmosphere. And perhaps if you have any interesting points there, we'd be very happy to chat. Yeah, thank you.
Thank you for a great talk. Questions? Question there in the corner.
Hi, Takamasik. This is really great. So you had your magic KZZ that changed the temperature profile and changed the methane mixing ratio.
Yeah.
And very interestingly, you needed different KZZs to match the temperature profile versus the mixing ratio. Can you talk a little bit more about the various KZZ prescriptions that you used?
Yeah. So, in this case, what we did was, because Titan has been extensively studied, so the different eddy diffusion profiles were taken from different literature sources. And some of them are actually obtained by fitting a diffusion model to nitrile, some of them to different other chemistry. Because these different, you're looking at, by fitting this into different abundances, they're sensitive to instruments and when you're observing and so on. So there are differences in the KZZ profiles because of that. And of course, when we use those different profiles in the temperature, because we are doing energy balance, in this case, we are also kind of reliant on the chemical network itself, but how much of the chemistry is pumped up, for example. And then, of course, it depends on rate constant and so on. Whereas the temperature also depends on thermal conduction as well, so also the heat flux, whereas the chemistry doesn't. So there is slight differences because of that, yeah.
Other questions? Maybe I can ask a question. So if this Titan would be actually losing methane, would you expect some sort of a methane tail that you could actually observe in some other way?
I think the argument for Titan losing methane is not in a hydrodynamic sense, but perhaps more than what is expected from simple genes escape. So that's and that was kind of suspected because in the early days a diffusion model was fit to the data, and then of course you then get a diffusion limited escape, which is overestimating how much escape there is happening. So now when we try a physical model, then we do see that that's actually not the case. You're overestimating the escape, and that's probably something that is worth looking in exoplanets as well. When you apply a proper physical model, how does this disagree with those empirical determinations? Yeah.
Okay, let's thank the speaker again. We move on to Emma Postolek, locally from Groningen. They're going to talk about atmospheric evolution through ingassing and escape on young rocky exoplanets.
Hi everyone, so I'm Emma, I'm working here in Groningen with Tim, and today I will talk to you about which are the best songs to pick up for tonight for karaoke. No, this is for tonight. So today I will talk to you about how we investigate outgassing and escape on the study that we're about to submit very soon, where we investigate atmospheric evolution through the outgassing and escape on young molten rocky exoplanets. So just a bit of context before I start. So rocky exoplanet population, more than a third of the confirmed exoplanets today are believed to be super Earth or terrestrial planets, and that's what you can see here on this mass radius diagram. Some of those planets are plotted here, and they are colored by their equilibrium temperatures. And the one that we are interested in are the ones that are like in red or purplish, because their equilibrium temperature suggests that they are in a magma ocean stage. And for those planets to be in a magma ocean stage, there is different evolutionary pathways. And for instance, the planet can be a baroque, so no atmosphere, but still be in a magma ocean stage. Or the planet can host a very thick atmosphere, being in a runaway greenhouse states that maintain hot temperature close to the surface and be in a molten stage. And as most of you knows, there is a lot of interaction between the mantle and the atmosphere, and that's what you can see here on this scheme. So this is a scheme of the internal structure of a planet, and you can see that there is a lot of feedback between the interior and the atmosphere of those planets, because some of the volatiles that can be dissolved in the mantle can be outgassed during the evolution of the planet, but can also be locked up in the interior. and another processes to take into account when you model the evolution of those planets in atmospheric escape. So here's the evolutionary figure that I assume many of you know already. So that's why I only focus on this part because it's the one I'm interested in. And so it's a part of evolution where you have the magma ocean that crystallize, and you can see that at the same time, atmospheric escape happens. So it's important to take both into account outgassing and escape at the same time when modeling evolution. And with all of this in mind, we're trying to ask ourselves, how does the composition of secondary atmosphere arise on very irradiated planets? And to try to answer this question, we use the Proteus code. So Rob Calder, that gave a talk on Tuesday, already presented the framework. So I'll be quick. But Proteus is a couple atmosphere interior framework to simulate the evolution of rocky exoplanets. And we use a different module for this. So you see, we resolve the evolution of the mantle here using spiders. So we also include in and out gassing at the surface between at the interface between the mantle and the atmosphere. Then in our study, we try to compare the different atmospheric treatments. So using a radiative convective atmosphere versus a fully convective atmosphere. Then at the top, we include escape. And here we use energy limited formalism. And then we also evolve the star, especially for escape. So now let's jump to the results. So first thing we wanted to look at was the impact of atmospheric escape on the evolution of the magma ocean. And that's what you can see here. So here, I plotted the result, the evolution for two simulations, including atmospheric escape with the solid lines versus no escape with the dashed line. The top panel shows the surface volatile partial pressure versus time on the x-axis, and this panel on the bottom shows the mantle evolution. And you can see that when you include escape, so those cases, the mantle solidifies quite quickly after 3 megayears at the same time where all the atmosphere is removed. But when you don't include escape in your simulation, you retain a CO2-dominated atmosphere, and the planet is still in a permanent magma ocean state. So the point I want to make here is that when you include atmospheric escape, this can drastically accelerate the magma ocean solidification timescale. So that was for the first thing we looked at. And the second thing we looked at was the impact of the atmospheric treatment on the magma ocean timescale. And that's what you can see here. So here you have a PT profile of the atmosphere on the top panel, and the interior in the bottom panel. And so the solid lines here shows you the simulation with a radiative convective atmosphere treatment. And the dashed line here shows you the model where the atmosphere is fully convective. So if you focus on the one with Agni, so radiative convective atmosphere, you can see that at the beginning of the simulation, the planet starts really hot, and then you cool down in time near to the surface because of the radiative layers. And then the interior cools down as well. And then you end up with a solid interior, so the mantle solidifies quite quickly. And when you include atmospheric escape, intense atmospheric escape, your atmosphere also escape at the end of the simulation. But when you only use a fully convective atmosphere, the planet seems to be in a steady state for almost all of its evolution, and at the very last time step, intense atmospheric escape just remove the entire atmosphere. But the interior of the planet stays molten for the entire simulation. So the point I want to make here is that if you use a radiative convective treatment of your atmosphere, it can also speed up drastically the magma ocean solidification timescale. So this was for a comparison between two different simulations. And after this, we wanted to run bigger grids of simulation, and that's what I display here. So here we ran about 2,000 simulations, trying to investigate the influence of different parameters like the stellar mass, the initial volatile budget, and the influence of different escape parameters. And here I show the influence of the magma ocean, the oxygen fugacity on the final mean molecular weight of the atmosphere. And so you can see that, for instance, if you start with a very reduced mantle here with the blue curves, you end up most likely with a very light secondary atmosphere. But when you start with a very oxidized mantle, here, the red curves, you end up with a very heavy secondary atmosphere. So here, this shows that the composition of the secondary atmosphere is mostly dependent on mantle redox state. So that was one of the parameters we tried to investigate, and we also investigate the influence of the initial carbon budget of the planet, and that's what you can see here. So here, this is a plot that shows you the final dominant atmospheric species frequency in the grid, and the top panel shows you 3 different oxygen fugacity that we tested, and also 3 different C2H ratio. And the first thing that you see when you look at this plot is that there is first a wide variety of composition for this secondary atmosphere that arise from our simulations. And if we look a bit more into detail, for instance, here, when you look for reduced mantles, so those kind of simulations, you end up mostly with H2-dominated atmosphere or CO-dominated atmosphere. When you start with a very oxidized state here, you end up mostly with a water-dominated atmosphere, or also CO-dominated atmosphere. And then for the influence of the initial carbon budget here, if you start with a very low carbon to hydrogen ratio here, you end up mostly with water-dominated, hydrogen-dominated atmosphere. And if you have a high C2H ratio here, you also end up with mostly H2-dominated atmosphere, but also CO or CO2-dominated atmosphere. So another parameter to take into account when looking at the influence of the volatile budget, initial volatile budget of the planet on the final composition of the secondary atmosphere is also the initial carbon budget. And then we wanted to see for all of these parameter where we tested the initial volatile budget of the planet, which one was the most impactful. And that's what you can see here. Here again, I showed the oxygen, the initial oxygen fugacity of the mantle. Here on the x-axis, this is the C2H ratio, and here the semi-major axis of the simulated planet. All the points are colored by the final mean molecular weight of the atmosphere. And the first thing you see is that the gradient of color is stronger on the y-axis, so in this direction rather than on this direction, and that means that the oxygen fugacity is the most impactful parameter when looking at the final composition of secondary atmosphere. And then looking at this plot of our parameter space, we try to see if different regimes arise from our simulation. And for instance, if you focus on very close-in and oxidized planet with a high C2H ratio, you're most likely to end up with a CO2-dominated atmosphere. If you are also close-in but with a very reduced planet, you end up most likely with a H2-dominated atmosphere. And for instance, what we found very interesting was that if you are a planet at the same semi-major axis as the Earth here, and you start very oxidized, in our simulation, we saw that the planets either end up because they reach radiative equilibrium here, and they are most likely dominated by CO2. And if the planets end up the simulation because the mantle solidified, it's mostly a H2-dominated atmosphere. So that was our results. And to conclude, I hope with this presentation I convince you that the magma ocean solidification and escape together are very important when modeling the atmospheric evolution of rocky planets. And among all of our simulations, we had a wide variety of atmospheric composition, ranging from hydrogen-dominated to SO2-dominated atmosphere. But most of our simulation end up water-dominated. Thank you.
Thank you for a great talk. Questions? There in the middle.
Thank you very much. Really great talk. I'm Mei Wu from Freie Universität. I have a question about magma ocean solidification. What kind of temperature range do you use? Like, how do you decide which part of the mantle is solidified?
Maybe I can just come back to the, oh no. For instance, here, so this is the interior, and you see that, so for all of the simulation we run, we decided to start with a fully molten magma ocean. So a very hot planet with like a surface temperature around 4,000 Kelvin. And then how the mantle solidified in time is depends on the liquidus and the solidus that are implemented in the interior dynamics module, which is called SPIDER. And for this, we use the liquidus and solidus are defined for NGSIO's three species. I don't know if this answers your question or...
Yeah, it does. Thank you.
Okay.
Other questions? Maybe I can ask a question. So you talk about that the outcome may be CO2 atmosphere or H2. What about N2? Is that an outcome of one of your schemes? Or?
Yes, but we don't have a lot of N2 atmosphere. So it's a bit hard to see, but I think, yeah, N2 here, it's in purple, and you see that it's only a very small fraction of the simulation that end up with a N2 dominated atmosphere. Most of our simulation are H2 or CO or CO2 dominated atmosphere. Nitrogen is a small fraction.
So we are actually lucky or unlucky?
Yes,
okay.
Very lucky.
Anybody else? Yes, there.
Hi, Philipp Baumeister from Freie Universität Berlin. What are the pressure ranges you get for these atmospheres? So what are the pressure ranges you get for these kinds of atmospheres you end up with? It's like the hundreds of bars and the tens of bars?
Yes, maybe I can show an additional plot. Okay, it's a bit intense. But if you look at this column here, this is the surface pressure that we end up with in the grid that we run. So all of the different panels correspond to one of the parameters that we tested in the grid. And here you see that we go from 1 bar up to a few thousands of bar for the different atmosphere that we end up with in the grid. Yeah.
Thank you.
Okay, thank you. Let's thank the speaker again. The next speaker is Laura Kreitberg from MPI Heidelberg on how common are exovenuses.
First ones were a bit over my head.
Should practice my karaoke song. All right, hello everyone. My name is Laura Kreitberg. I'm from MPIA in Heidelberg. And I'm here to try to answer a very simple question. Are exovenuses rare? And since I know we have a diverse audience with a lot of different expertise, I want to start out by being specific about what I mean when I say exovenus. To me, as an exoplanet person, Venus is any planet that is rocky with solid surface and a thick CO2-dominated envelope, so something like 100 bar. So this is not exactly Venus. It can be hotter than Venus, but not so hot that the atmosphere is melted, that the surface is melted. It can be more massive or less massive than Venus. It can have a different type of host star. So I put a Venus emoji to illustrate the level of specificity that I'm talking about. So I don't think I need to stress too much why exovenuses are interesting. I'll just say it's great that we have at least one example from our solar system where a Venus was an outcome of rocky planet formation and evolution. We also just heard beautifully from Emma that you can get thick CO2 atmospheres as a fairly natural end member scenario from planet formation. It's not at all the only case, but it's say easier to get a thick CO2 envelope than it is to get a planet like the Earth. And as an observer, We love these types of planets because they are very observationally feasible. So we heard about this already from Hannah and Brandon and Johanna earlier on Monday, but just to wake everybody up on Thursday afternoon, JWC has been transformative in our ability to study the atmospheres of real rocky exoplanets. Our sample is a couple dozen systems, so it's more than 10, it's less than 50. They typically have very short orbital periods between about 1 and 10 days. They're transiting typically very small host stars, so M dwarfs between about 1/5 and 1/3 the radius of the sun. And we like to study these by transmission and emission spectroscopy. Here you're seeing a transit where the light can filter through the planet's atmosphere if it has one. I'm not going to focus on that because most of the transmission spectra results are too preliminary, I would say, to really say yes or no, these atmospheres are Venus-like. What I am going to focus on is emission spectroscopy, mainly for observations when the planet goes behind the star. And so you get a measurement of the temperature of the planet's day side, as we heard about from Hannah in detail. So we already saw this plot, but I'm wondering a bit if it went by quite quickly for folks who are not exoplanet atmosphere aficionados. So you guys who already are like Rocky Worlds experts, you don't have to pay attention right now, check your email. But for like the disk people and the Earth interior people and the planetary scientists, this is for you. So the way we contextualize measurements of the dayside brightness temperature of these planets is to compare their dayside temperature to the maximum possible for a bare rock. And the idea here is that if your planet has no atmosphere, all of the incident stellar radiation lands on the planet's surface and it can be re-emitted directly. By contrast, if you have a thick atmosphere, it's good at redistributing heat from the day side to the night side. And so if we plot the temperature relative to the theoretical max for a 0 albedo bare rock, we would get something like this curve up here. But then if you put a thick atmosphere on there where thick means 10 to 100 bars, you move this temperature down to the dotted line. And then, as Hannah also said, real atmospheres can have absorption features, and CO2 in particular is a really strong absorber. And so here are some model predictions for a pure CO2 envelope of about 10 bars. And you get what Hannah nicely called the CO2 bonus. So here you can see that the day side is even colder because of the strong CO2 absorption band. The reason for this is that for an atmosphere that cools as you go up, we can't see very deep down because CO2 is so opaque. And so that means we're seeing a thin or a cold upper layer that increases the contrast between a bare rock case and 110 bars of CO2 down here. Does this make sense to everybody? Yes. Okay. Let's put some data on it. So we saw this already, but I want to focus specifically on how the measurements compare to these predictions for a Venus-like atmosphere. And you can see the planets are all, just about all, really, really hot. So they're clustering up here. This blue line is an average fitted to all the data points. It's about 95%, the theoretical maximum. For almost all cases, I'll come to this one in a second, Venus-like compositions are significantly ruled out. Astronomers love outliers, so I just wanted to quickly address these two, since the people responsible are here in the audience. So we have one case that's hotter than the theoretical maximum. Please talk to Eric about that. Eric, I see you back there. My observer sense says this is probably just random scatter, so Poisson noise is pushing this higher than the theoretical max, rather than something astrophysical. This case down here, LHS 1478b, is super interesting. I made the point semi-transparent because, sorry, Fleur, because I think this is still unresolved. The data was complicated. There's some instrument systematics. Prune has more observations. And so if you're interested in seeing how this is developing, please come talk to her. She's right in the front. But aside from this outlier here, I think the most robust thing that we have learned from these measurements for all of these other planets is that they do not fit the Venus-like model. So I can only speak for myself, but I was a little bit sad about this because I'm on team atmosphere. I want to find atmospheres on these planets. And so there have been like many different feelings about this. And I would say where we are right now is in the bargaining phase. And the way this looks in particular right now is playing around with the temperature profile of possible atmospheres. And so the Venus-like models that I showed are all assuming a temperature profile that looks like this. So the temperature is decreasing as you go higher up in the atmosphere. But we know that it's possible to get thermal inversions or stratosphere. We see this in the solar system. We see it in Earth. The ozone is heated up in our upper atmosphere, and so the temperature actually increases as you go up. We've seen this for exoplanets as well. And this can be caused both by atoms or molecules, but also by clouds or hazes. And so I would say a really interesting area of study at the moment is to try to guess, try to model, are there any candidate absorbers that you could put in a thick CO2 atmosphere and heat up the photosphere to the level that we actually measure? And the really short answer is not that we have found so far, specifically for the case of a thick CO2 envelope. So I'm showing on the left here preliminary results from self-consistent modeling from Jae-Guk-Lee. And the punchline is that we tried a bunch, we tried to look at some limiting cases of, say, like a shiny condensate and an absorptive condensate. And no matter what we chose, none of the ones that were plausible in a highly oxidized composition would heat up the atmosphere to the extent that we observe. So I think where we stand at the moment is that kind of no matter how cute you get with your modeling, a thick CO2 composition is probably not going to explain the measurements so far, at least for 8 of the 9 planets that have been observed. A question I get a lot is like, what about other kinds of compositions? It's not necessarily CO2. That's a totally fair point. I think that so basically the lower your surface pressure is and the less CO2 you have in your atmosphere, the better a fit you can get to the observed data. But if you take a simple Occam's razor approach and say, what is the simplest model that explains the measurements so far, you can get a good fit to all of these data points except for Prune's mystery point. With a simple model assuming 0 redistribution from an atmosphere and a fairly low albedo bare rock. So that brings me to my conclusion slide. I feel like it's a kind of a power move to coin a problem, but I did this to get your attention. So I'm calling this the missing CO2 problem. Where is the CO2 in these atmospheres? Why do they not look like Venus? And we've already heard a couple of possible solutions to this problem. Maybe they're forming without a large volatile inventory. Maybe the CO2 is trapped somewhere in the interior, so it's just not getting out to the observable atmosphere. Maybe it did get out and it escaped. Maybe it's some combination of all of these things. But I think this is I found this a very, very profound result from the early JWST observations. And I hope that it spurs some debate and discussion for the rest of this week. Thank you.
Thank you, Laura. Questions? Completely in the back there, in the corner.
Bennett Skinner, McMaster University. Just out of curiosity, where would the Venus go on the plot you were showing with the exovenuses?
Thank you. I forgot. So Venus is almost exactly right here at about 2 times Earth insolation. So most of the sample indeed is hotter than Venus, but TRAPPIST-1c, work from Sebastian Siebe right in the front row, is almost identical to Venus in terms of size and equilibrium temperature.
And in the T-day over T-day max, like if we.
Oh, Venus itself. Oh, Venus is down here. Like the clouds are so shiny that it's very, very cool if you were to measure it in the same way that we did for these exoplanets.
Okay, thank you.
Other questions? Yeah, please.
Sorry, question from the question person, Limbo Christmas, Uppsala University. Really enjoyed this talk. This is exactly like my favorite kind of science. I was just wondering, out of these stars, maybe I should kind of know this, but how does that stack with like stellar metallicity? Are they kind of similar stars?
Oh, that's a really good question. I mean, I know that metallicity is hard to estimate in a robust way for M dwarfs, but I couldn't tell you if are they more metal rich or not. That's a good question.
That would be interesting. Yeah. Thank you.
Maybe I can ask a final question. What is there anything maybe special about LHS 1478 that makes this?
Yeah, I don't know, Prune, what do you think? Is it
I mean,
something weird?
but is it actually bigger than the other? Is it more massive?
It's not, I mean, it's like, I don't know, I think we need maybe some good evolution engineering modeling to find some answers and also just for data, but it's not particularly, there's nothing that I would say right off the bat makes it particularly unique.
Yeah, for folks online, been saying there's nothing off the bat that makes it particularly special.
Okay, let's thank Laura again. Okay, for a final talk, I understand that Tuhin Ghosh could not make it, so but Oliver Schottel is happy to stand in and give the talk on his behalf. And it's about reaccretion of giant impact ejecta.
Thanks very much. Sorry, everyone, that you're hearing from me again. Yeah, like we heard, Tuhin, unfortunately, at the last minute wasn't able to come to the meeting, but it's a fantastic postdoc working with Mark White and I at the Institute of Astronomy in Cambridge. So it's a real privilege to present his work here. Here is Tuhin when you see him at the next meeting. So please do talk to him, and his paper, I'll show the link at the end. So we've seen a lot about the cosmic shoreline that came up very early in the meeting this week. And fundamentally what this is pointing out is the relationship between planet mass and its cumulative energy it's received from its host star, and the potential consequences of that for the atmosphere of planets, and this sort of empirical relationship that objects in the solar system, if they're small and have received a lot of integrated energy from the star, may well have lost their atmospheres. And so, yeah, fundamentally, it's this basic relationship between a property of the planet and a property of the star, cosmic shoreline. But I think if we kind of take our minds back from the cold January of Groningen to maybe 6 months ago when we were enjoying summer on the beach, we know that the consequence of that indulgence is not only sunburn, but other things can happen. And beaches are not defined by sunburn, but also by sand and rocks. And in the presence of my kids on a beach, they'll be thrown at you in abundance, and you'll discover there's a lot more going on than just sunburn when you leave the beach at the end of the day. And so what we're interested in here is the shoreline not only defined by light from the star, but the shoreline that's defined by rocks. By impacts to the planets.
We're having problems with it's not showing up on the screen.
Oh no.
Fix the slides, sorry.
Yeah, so what we want to, and in fact, if we go back to the Zanley paper, so the Zanley 2017 paper, which this figure's from for the cosmic shoreline, they also have a figure later on kind of drawing another shoreline, one defined by the impact velocity of material accreting to planets. So this is just to say that empirically, you could put a line through these data that distinguish the presence or absence of an atmosphere, not only from the integrated energy deposited by solar photons, but also the energy that might have been the integrated energy that's been received by impacts over the course of planets. And both of these processes together can contribute to atmospheric loss. And so the presence or absence of atmospheres that we see today. So there's more to shorelines than just the photons. And we know impacts are an important process. We had that, okay? We had that, in a few talks earlier this week. The solar system planets evidence this, or at least suggest it. Uranus, the dichotomy on Mars may be related to impact events, Earth's moon, and Mercury. Obviously, many of the popular scenarios for explaining a dense Mercury rely on an impact erosion event of the mantle of the planet. So impacts seem like an inevitable consequence of a multi-planet system in the last stages of assembling these kind of rocky worlds. And there's also been work suggesting from the kind of architecture of exoplanetary systems, so this is looking at orbital period ratio, and in this study, pointing out a deficit of orbital period ratios in this region of the diagram, and that's linked in this case, argued to be linked to instabilities, dynamical instabilities, events that would themselves trigger giant impacts and potential, a potential restructuring of both the system and then the composition of exoplanets in response to the impacts that are triggered. So what we're going to look at in this talk, just briefly, is the efficiency of those impact processes for driving atmospheric escape. This is a really nice figure from Hilke Schlichting's paper from 2015. What it's showing is the efficiency of mass ejection as a function of the mass of the impactor. And there's this curve here, and the efficiency of atmospheric erosion peaks at quite small impactors. So what this is saying actually is that the really big objects, like the giant impactor itself, is actually relatively inefficient at driving atmospheric escape, because it would lie right down here, a big kind of Mars-sized object hitting a planet. It ejects only a tiny fraction, compared to its mass of the atmosphere of the object it's hitting. So actually really efficient erosion is driven by small objects. So what we're going to look at here is an additional process. So we're going to think beyond the single impact event and think about the debris that's launched from the impact. So this is an SPH simulation, and really the point of showing this is just to illustrate that a lot of stuff is thrown off of the planet in an impact. And many impacts are not purely accretionary. They also eject material on orbits that are not bound to the target planet. And it's that debris that's launched from an impact event which we're going to consider in this talk, and as an additional mechanism for driving atmospheric escape that's previously been a little bit underexplored in consideration of the efficiency of impactors at sculpting planetary atmospheres. So this is a figure from Alan Jackson and Mark Wyatt's work from maybe 10 years or so back now. And what they've shown is if you've got this impactor event here, very, very quickly, the debris launched from that impact event forms an annulus, it's kind of attached to the planet there. But it's an annulus of debris, which over time will do two things. So it spreads out around the orbit. There'll be collisions between the debris, which will cause it to get smaller, grind down, and eventually be blown out of the system. So that's one thing that's happening. And the other thing that potentially happens is it's reaccreted to the planet that it's just been blasted off of. And it's that reaccretion we're interested in. So yeah, the question we're going to ask is, how does ejected debris affect atmospheric erosion efficiency? So yeah, let's imagine that's our planet. And how does it feel about this? So the model is a kind of fairly sort of simple parameterization that Tuhin assembled for the paper. I'm showing the equations just to highlight really two kind of important things. We've got two timescales that we're really interested in here. What's the timescale for collisions between the debris that's ejected, because that's going to grind it down and cause it to eventually be lost from the system. And that's competing with a timescale for reaccretion to the planet. So if we can reaccrete it quickly, it's going to be able to drive atmospheric escape. So one thing to note is that there's a strong dependence on the semi-major axis of the planet, but it's the same for both timescales. So whilst the timescales get much longer at a wider separation, it doesn't actually change the ratio of these timescales. The other thing to say is that the accretion process is sensitive to the maximum size of the debris launch. So bigger objects stick around for longer. So there's the collisional timescale is longer. And it's got this inverse dependence on the mass of the debris. So more debris has a shorter collisional timescale. So let's look at the collisional evolution. So this is the mass of debris over time that's left, and it's got this kind of sigmoid shape. So in about sort of 5-ish million years, In this scenario where it's 1% of Earth's mass has been ejected as debris following a kind of moon-forming style impact, with the maximum size of the debris launched 100 kilometers, and it's a size distribution towards smaller objects away from that. In about 5 million years, that debris is half gone, basically. So that's one kind of time scale. The other time scale is the accretion, how much of that's actually accreted. So whilst the debris is collisionally grinding down, it's also being accreted to the planet, and 0.3% overall is accreted. So about a third of the mass lost from Earth in this giant collision is reaccreted to the planet over a few tens of millions of years. So what does this 0.3% accretion do to the atmosphere of the planet? It's hopefully what we're going to see next, if I can encourage some forward movement. Thank you. So we're going to be looking at the primary impact. So if you sort of take that sort of relationship I showed earlier, where giant impacts themselves are somewhat inefficient, thanks. The primary impact might eject about 10% the mass of the atmosphere. So a lot, but if you've got a 1 bar atmosphere, you've actually got most of it left after that, in principle. If we add the effect of reaccretion on, that actually relatively small amount of mass that's reaccreted in a very short period of time, in only a few million years, erodes the entire atmosphere. So this is calculated for a 1 bar modern Earth-like atmosphere, so relatively high mean molecular weight, just as a sort of nominal case. So reaccretion very rapidly and efficiently enhances atmospheric loss from these major impact events which we think are fairly sort of fundamental to the end stage of terrestrial planet growth. And actually across this wide range of parameter space, so semi-major axis and planet mass, so 1/10 to 10 times Earth mass, and this range of semi-major axes, the atmosphere is lost over this wide range of parameter space. So this process is moderately insensitive to some basic changes in the parameters. I just want to end by saying, kind of add a nuance to this. This is initially the calculations I've shown you have been for a scenario where the planet is isolated. Earth on its own gets hit by a moon-forming giant impact, and then gets hit again and again and again by bits of itself that were launched off and came back. In reality, we expect many planets to be in multi-planet systems. Earth itself obviously is. It's got Mars and Venus as near neighbors. And that's true also of exoplanetary systems. So the multiplicity of exoplanetary systems has been looked at frequently. With neighbors, they themselves catch some of the debris. So they also get hit by that boomerang and themselves then experience atmospheric erosion and sort of evolution driven by that debris, which is potentially interesting to think about. So it slows down the loss of atmosphere for Earth in this case. It still loses all of its atmosphere, but a bit more slowly. But actually it also means that Venus and Mars also experience atmospheric erosion and loss driven by Earth's moon-forming giant impact, which is interesting as well. So just to summarize, you can find more than UV at the cosmic shoreline, so it's worth thinking about. Impacts, reaccretion of impact-driven debris can add an efficiency factor essentially to atmospheric erosion. And it's good to have planetary neighbors. If you get hit by a giant rock, they'll protect you a little bit, but it's pretty bad for them. Thanks very much.
Thank you, Oliver. Questions? Yeah, there in the back in the middle.
Hi, Ollie. Matt Roach, University of Bristol. Thanks for the talk. How well do you think we know the size distribution of debris from a giant impact? So most of these impacts produce a lot of vapor, which I would expect to readily condense into sort of a small distribution that maybe would be quickly redistributed out the way by the star. So I was wondering where we get those numbers from.
Yeah, that's a really good question. So the key point is that, like you said, if the debris ejected is really small, or if it's all in vapor, which it's the same thing, then it's going to be quickly lost from the system, and we don't have that reservoir of large objects that release the debris to provide the collisions and atmospheric erosion. So yeah, that's a key question. The SPH simulations, which we've looked at, both some simulations Tuhin's run and other simulations that have been performed, give an indication, but I'm sure you yourself know that maybe the ability to characterize the size of small objects in SPH simulations is perhaps somewhat challenging. So yeah, key question is the amount of solid debris ejected and the size of it. And it's something we've looked at. And to the extent we've dug into it, it seems there's evidence for, 10, 100 kilometer size objects being launched. But I think there's also a question then of the partitioning between vapor and solids in the ejector, and the extent to which the large objects are real or a feature of models that struggle to start resolving things at small scales. So I think those are all really good questions. The fundamental result is if you are ejecting solid material from an impact, it's going to have this extra efficiency in driving atmospheric erosion.
There's a question here on the stairs. Yeah. Oh, there's another question there. Yeah.
Hi, Andrea Zarzi from Stanford University. My question is, I might have missed this, but are you accounting for the ejecta that is escaping, that has like a escape velocity that doesn't make it reaccrete on the planet?
Yeah, so all the ejector is not bound gravitationally to the planet. It's in orbit around the star.
Okay.
Yeah, so it's escaping from the planet, but it's not escaping from the system as a whole.
Okay.
It remains gravitationally bound in the potential well of the sun, and ends up in an annulus in orbit around the sun, with a velocity dispersion defined by a factor multiple of the escape velocity from the planet. Yeah, thanks for asking that.
One final question here on the front.
Ready?
Hi, really interesting work. So you find that there's like no dependence on semi-major axis. If in an ideal world, this is the only mechanism driving atmospheric loss. So do you think it's like worth using that lack of trend compared to the classic cosmic shoreline to test this, or are there too many other factors like volatile budget to begin with that you don't know?
Yeah, that's an interesting point. So I sort of said there wasn't a dependence on semi-major axis, and in a sense in this model that's true. It is a simplified model, but what the model neglects is that the semi-major axis does introduce a massive increase in time scale. So such that by a few AU, I can't remember exactly the number, you quickly get to like giga-year timescales for the collisional evolution of the debris and then the reaccretion of debris. And at those timescales, additional processes probably ought to be considered, like gravitational interaction between the debris and other planets in the system, which isn't being captured here. So that's the caveat. But I think you're right in principle. If you thought that impact-driven erosion was, say, explaining the radius value, say, then you've got a testable hypothesis. Like, I'm not arguing it's explaining the radius value, but the radius value isn't defined by the presence or absence of atmospheres on really small objects. So this is sort of thinking about end-stage terrestrial planet formation. And if we end up with a radius value for those objects, then maybe impact-driven erosion has more of a role to play than for, say, sub-Neptune-sized objects. Yeah, thanks, Claire.
Okay, let's thank Oliver again. And let's thank also all the speakers of this session. And there's a small announcement about the singing this evening, or something?
Yeah, just a small addition to the karaoke announcements. The room that we rent is actually quite large. It should be able to fit the entire conference. And it's also a bar. So even if you don't like singing yourself, feel free to just join us and to watch the LSE and LSC embarrass themselves. And in addition, if you would like to bring a partner, we actually have a few additional name badges. So if you would like to bring someone, go to Giacomo of the LSE over there. And he will be happy to hand you out a blank name badge so that your partner can join. Please come back for the breakout sessions here at 12:30. 12:30.
All right, coffee.
Enjoy your coffee.